Cool, cool. And quick show of hands, sorry, and this will be the last show of hands, I promise. I know your arms are getting stiff. But quick show of hands, how many of you have ever built a circuit board before, like a real circuit board? Okay, so that's a pretty large percentage of the people in the room. In fairness to those people that haven't, I'm going to walk them through some things which might sound familiar to you. There'll be some anecdotal things which you'll pick up and say, oh, I guess maybe, well, hopefully you'll pick up and say, I never really knew why we did it that way, but apparently we do it that way, and now I know. So who am I? That's my Twitter handle, all of that stuff, GitHub, blah, 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 blah. You're more than welcome to contact me. I have my own Hackaday.io account. And Hackaday.io is this project site that we put together about a year ago so we could throw stuff in there. I was one of the first guys to put like a proper project in there, which is this little FPGA board. How I self-identify, I don't know. You know, I do a lot of embedded software, but I build a lot of boards. As I said, I shipped a lot of boards last year. About 150,000 BLE boards went out last year that were products that I designed. Do a lot of radio, do a lot of wireless. I'm a huge fanboy of that sort of thing. Big believer in social change through technology. So I do a lot of stuff, flood control systems and all sorts of crazy things like that, weather monitoring and all these other things for places that need that sort of thing. So these are all the sorts of things that I build. We'll kind of skip past most of that. So let's level set, right? So this is where everything kind of begins, right? How many of you use Arduino, like regularly? Okay. Okay. So this is kind of where it begins, right? Everybody's experience is this way, and for those people who raised your hand but have never really done this in a vocational way, right? Somebody paid you all day, every day to do this 40 hours a week. This is okay, right? And I have to emphasize that, like we all do this, okay? And that's something which is really important to emphasize because I think people have this tendency to think that, oh, well, professional engineers are somehow omniscient. We kind of know everything. We don't have to do any research. We learn all of these things in school. Oh, Maxwell's equations, I just fall back on them. There's actually a great quote from a guy named Kevin Morris who writes, amongst other things, something called FPGA Journal. And Kevin Morris had this great quote where he said, you know, engineers are in constant fear of being found out. And it's true, right? We're like just one step ahead. So I'm like 50.1% effective. Everything else, like I don't know. And that's okay, right? The reality is that there's a lot to the physics and the science of these things, and we're still very early days in some of this stuff. So this is actually where it begins. Now, the ESP board that I had built is a flasher, and we'll talk a little bit about that in a bit. I wanted to model getting this little ESP board up and running and connecting it into the computer and being able to flash it and doing all of these other things, which if you have any experience with embedded software, tends to be one of those very tedious but all too necessary tasks. I challenge you to set up Eclipse one time with a board that you don't have like a standard configuration for, and it can be painful. So, you know, I started off with something like this. Big mess of wires and that sort of thing. And I said, all right, you know, how do I condense that down into a circuit board? Because I'm going to have to do this every day. I want to plug this thing into here, and I want to plug this thing into here, and I don't want a bunch of crap hanging off of it. So I'd actually gone ahead and I'd milled out a circuit board on my milling machine, which is here. So this is actually a PCB mill. It's not a 3D printer. The people at other mill will be very excited at the fact that I emphasize that this is not a 3D printer. I do have a 3D printer. It is the most expensive ottoman I've ever owned. I rest my feet on my MakerBot, and my other mill creates a bunch of circuit boards for me. It isn't that there's necessarily anything wrong with 3D printing. I think 3D printing is fantastic, and I think it's moved a lot of things forward. But I think there has been a bit of kind of the boulevard of broken promises there with some of the early technologies in 3D printing. So I started off by going from the breadboard and actually milling out a PCB. And we'll actually talk a little bit about kind of the milling process a little bit later on. But I want to talk to you a little bit about this board. So I'm going to pass around a bunch of these. You can take a look at them, send them back to me, because we're going to need them tomorrow. It'd be real unfortunate if they all went walkabout. I don't think I'm supposed to walk in front of that speaker.
Feedback.
Now I hear what I sound like. I'm going to pass a bunch of these around. Just take a look at them. Just kind of pass them in various directions. So this board, this is called the ESP8266. Oh, awesome, thank you. This is called the ESP8266-01, and there's a bunch of different flavors of this board. There's a 04, 03, 02, it kind of all makes sense, but some of them have little castellated edges on the side of them, so they actually don't have pins on them. You just solder to the pads on the edges of them. I chose this one because it's easy. Because it's got some pin headers on it, it makes it easy to connect it into a connector and then do something with it. I will tell you that by the time we're done flashing it, that's really all that you'll need to do something. So if I wanted to turn on a light, activate a motor, something like that, it's a reasonably small little module that can do some pretty impressive stuff, and it can be Wi-Fi controlled. So I'll actually show you how to set up a web server on it. We'll set up a little web server, and we'll actually log into it and just toggle a GPIO and that sort of thing, turn a light on and off. And we'll do all of that using Node.js wrapped up in Lua rather than having to do deep embedded work where you've got to figure out how to set up tool chains and all that other stuff. So the ESP, really low-cost Wi-Fi module. It appeared a couple of years ago, actually, on the market. For the longest time, it hadn't passed FCC. Just about a year ago, it really started to make its way over to the States, and then eventually it did, in fact, pass FCC. There was a revision on the chip itself before it passed FCC, but now that it's passed FCC, you can buy these little modules from Adafruit. You can buy them all over the place on eBay and things like that. Amazon's got them. I ordered like 20 of them on Amazon the other day, and that's actually what's running around the room right now. And they've got a couple of different ways that you can interface to it. You can write applications directly in C, so you can follow a traditional sort of embedded workflow. You can also use AT commands, which, if you're old enough, I unfortunately am, you know what AT commands are. So AT commands, we used to use a lot with traditional modems. You know, that modem, right? So AT commands you pass over a COM port, right? So you send it over serial, over a UART, and you send AT commands to this thing, and you can set up a web server, and you can give it an SSID and a password and all of these other sorts of things, and you can set up the device using AT commands. The nice thing about the AT commands is that you actually have a UART or a COM port interface that's actually on the Arduino, so you can plug this thing into Arduino and actually configure it from that, okay? This is actually the really interesting thing, though. The use of Node MCU. It's fairly recent. It's not hugely recent, but it's fairly recent. Some folks put together a library which basically flashes the device with a Lua interpreter. And what that means is that the sort of base level of the device itself, I can pass it a Lua file. Inside of that, I've got Node.js, and that script executes line by line, just sequentially. And, you're all right. It executes line by line sequentially, and I can set up things like a web page that interfaces to that device, that sort of thing. So that's actually what we're going to get at today. The cost for the device itself is extremely cheap. As I said, if you go to Taobao, which if you don't know what Taobao is, I encourage you to learn to use Google Translate and then use Taobao. It's kind of the Chinese equivalent of eBay, but it's not really eBay. So you'll find a lot of commercial vendors will actually have a proper storefront set up in Taobao. And the experience that I found, I would go to these markets, the very famous, Shenzhen and Shanghai and Beijing electronics markets that everybody talks about with great affection. You go to the markets and you realize that the market is really just a bricks and mortar front end for people who have a Taobao store. And Taobao is the means to sell you things over the internet, which if you believe e-commerce doesn't exist in China, man, it's huge. Like everything is bought off of Taobao, right? So using Taobao, you will find that those guys will actually ship over to the States as well. Doesn't matter. When China Post is going to come, it's going to come. And they're going to put something in a box, and they're going to write an address on it, and they're going to ship it. And if it gets to you, great. If it doesn't get to you, you know, shame on you for trying to import something and not wanting to pay customs on it, right? At the end of the day, there's nothing sinister in that. It's just kind of a fact of life. But I can tell you that I've had great success, and I don't know that I should say this on a live stream, great success bringing electronics into the country. Yeah, that's probably not the best thing to say, was it? ESP8266, one of the downsides to it is that it is power hungry. But like anything, so when you're dealing with wireless, power consumption is usually related to its transmission, right? Because you want to try to get as much signal out there. So its peak current can be up to about 400 milliamps, which is reasonably high, okay? Your USB port is only capable of giving you 500 milliamps off of a single USB. The 400 milliamp requirement is actually reasonably high. So actually, we'll put a little power supply together too, which will give us a better means to actually power the ESP as well. So we'll use a little regulator circuit, and we'll tidy it up with a regulator that allows us to power this. It doesn't have a lot of GPIO on this module, but the chip itself does. So the chip itself, I mean, it doesn't have a huge amount, but it's got 10 or so GPIO that are actually on the chip itself. That means that the chip is useful. Other versions of the module, I've got a bunch of other ones up here, will actually give you a lot more IOs, so you can actually interact with a lot more devices from it. So there's also an Arduino library available for the ESP8266. It's a brilliant library from the folks at Adafruit. I would strongly encourage you that if you want to interact with the ESP8266 and you're familiar with Arduino, that's the place to go. Okay? So getting started. Here's what we need to do, right? I need to get an ESP8266 module. Check, I have those. Buy, borrow, steal a USB converter, USB to serial converter. And what that does is it turns your USB port into a COM port, or what we call a UART, okay? That allows me to interact with the device and flash the device with new firmware. When I flash the device with new firmware, then I can introduce new functions to it. Then I program something on top of that, right? So I've got one layer, which is the underlying firmware. Then I've got another layer on top of that, which is my application code, which is what I'm actually going to run on the device. Need to figure out what other components we need. Breadboard the connections, I already did that. I'll walk you through some of that stuff. I wanted to shortcut the process. And the genius thing about shortcutting the process these days is that there's a lot of open source hardware that's out there. So you can go to most places, Adafruit, Seed Studio, SparkFun, all of those sorts of places. And if you need a schematic, and it's a board that's somewhat popular, ESP8266 is super popular, you can usually find a schematic for it. This is actually from the guys that did Node MCU. They built their own programming board for it. This is from Adafruit. That was just a cursory search of the web, which was, I want to know what connections I need to connect into this device right here. Like, how do I connect to it? So as an engineer, am I omniscient? No, I use Google, right? It's like a software engineer, you know, how many Stack Exchange windows do you actually have open? We were at TechCrunch last week, and somebody had actually put together an application which was an organizer for all of the Stack Exchange windows that you currently have open. And it grouped them by some sort of functional area. Like, oh, and this is the Node.js collection, and this is the MongoDB collection, and this is, you know, it was, yeah, anyway. I found it amusing. So I breadboarded this, and this is actually the original breadboard, or one of the variations of the breadboard for this. Yeah, I had some issues early on in the process. You know, I wanted it to look like this, right? And this is software called Fritzing, which I'll show you in a quick second. Fritzing is kind of cool. It allows you to model things on the breadboard and actually draw a picture, right? So that's what I hoped to make. That's what I made. And there's this great scene in The Simpsons. Sorry if you don't watch television or The Simpsons or something. But there's this great scene in The Simpsons where Homer buys this kit to make a grill. And you see this amazing image of the grill. And it's actually him looking at the picture on the side of the box. And then he turns this way, and then you see this, which is like what he actually created. And it was supposed to be like this, you know, in-ground grill, that sort of thing. So Fritzing my cables and wires and all the other shit that went along with it. So just to, for those of you that haven't seen it before, sorry, that's a message to the NSA. So for those of you who haven't actually seen it before, fritzing is kind of interesting because it actually, it follows that same sort of, bloody hell, there we go. Now I've got two screens up. Let's see. I'm not going to be able to open it. I got to find where the software is. Anyway. Fritzing is kind of interesting because it allows you to model things on a breadboard fairly well and actually create a diagram which makes sense. Sort of visually, you can kind of work through some of these things. And it's that sort of, measure twice, cut once sort of thing. I don't know that I would necessarily use it unless I was writing an Instructable or something like that. But I did use it, and I thought it was kind of cool. It was a good experience. I think it's useful. It might not be the most useful thing, but it was useful for me. So software tools for the ESP, and I'll share all the slide deck with you so you guys will have access to it. There's a couple of things that we need. First of all, we need the Node MCU flasher. So basically what that is we need some means to flash this device. And if you think about the device as having really two component elements of software that are going to run on it, right? We're going to have one layer of firmware. Okay, and on top of that is actually going to be the program code that we're going to ask it to execute. If we want to use Node MCU, then we're going to flash it with the Node MCU firmware. If we want to use AT commands, then we'll flash it with the AT command firmware. Okay. One step up from that is the program that I'll actually flash on top of that, and that program will be just a simple web server that allows me to toggle some LEDs. But that's the basis for doing lots of cool and interesting things. So getting that connectivity set up, you'll see, is like 40 lines. It's amazing how clean and efficient it is. The other thing that we need is obviously the firmware. Both of those are available on GitHub, as is the Node MCU flasher. We need there's a really cool piece of software. It's actually not explorer.ru. I'm misleading you there. It's ESP8266.ru. But some guys in Russia had put together a really cool way to interact with the device and sit there and basically type in a line of JavaScript and ask it to execute, and it would just do that. And it's actually really cool because it allows you to kind of iterate on, hey, will it do this? And I wonder if I can make it do this. So you can actually create little snippets of code and say, run this snippet of code. Oh, okay, yeah, that snippet of code does this thing. It's kind of a nice, easy way to kind of ease into it. And as you go through that process, kind of unit test your way through a lot of little functional elements. Optional stuff, if you're going to use AT commands, then you're going to want a terminal of some sort, something that allows you to talk to the AT, or talk to the UART, the COM port. You can also do the same thing using Arduino. So Arduino has this COM port interface, serial port interface on it. You can just use that to do AT commands. You don't have to use Arduino. They have a software serial version as well. Yeah.
Will this be available for your?
Yeah. So I'll make all of this stuff available, and I'll actually take you through most of it today.
Okay, very cool.
Yeah.
Last week I became familiar with 1, 2, 3 circuits.
Yeah, so there's a whole host of those. Actually, next week, shout out to my friends at Altium. Next week, Altium, who builds this very high-end, sort of expensive schematic and PCB tool, are actually releasing a free version called Circuit Maker, which is actually due to be released next week, or announced and released in an open beta starting next week at Maker Faire. So that'll be timed with that, and then you'll be able to go to the website and just register for it. This is when the fever changes to warmth. I can take off the jacket. See, it all comes back around. So like that Circuit Maker is actually really good. It's got schematic hierarchy. It's got, unlike Eagle, it's got like clearance constraints in PCB. And like, I can't just run a track over the top of another track. And If you've ever used Eagle for any length of time, you'll be annoyed by all sorts of things. If you've only ever used Eagle, you might not know that they suck, but I can tell you, having written CAD tools in the 90s, we've come a long way since then, some of us. Sorry, I should be nice. Arduino, CPU, something like that with the UART, so we can actually talk to it over AT commands as well. Programming the ESP firmware is pretty straightforward. This is actually a shot of the flasher, and we'll go through all of this, but I just want to give you a quick heads up. So, this is actually the flasher. You go and download whatever the file is that you want to flash onto it. You open up the flasher, you point to the COM port, and you say, hey, flash this device. But there are some caveats to that, particularly if you want to use it with Arduino. Arduino is a 5-volt board, right? So other than the DFTWARE, which is 3.3 volt, all of the other Arduino boards are 5 volts, so their I/O voltage is 5 volts, which will actually drive the ESP8266 too hard because it's 3.3 volts. You'll fry the device. So there are some things that we'll do to kind of mitigate that. Throw in some voltage divider in there just on a transmit side of well, the receive side actually on the ESP, but the transmit side from the PC. And just kind of chop that down so it's at a reasonable level. That'll give us the ability to flash it. Because we're not going to keep it under that configuration for any length of time, that should be okay. We don't have to put level translators in there. And then we'll have this thing which is actually able to do all of the fun and amazing things which I said it could do. Running your own programs, this is actually the EXplorer, and sorry that you can't really see the text on the screen very well, but you'll see this interface later. So basically you write JavaScript, you click run, and it just does it. And it runs it on the board. And that's really cool. It's like super convenient. And so what it does is over the serial to USB, jumps in there, executes that on top of that Lua interpreter, which reads that script file one line at a time. Then you can actually flash the device with your program. It'll store that in ROM on the device, and then when the device, then I can pull that off of the programmer, and the next time that the device boots up, it'll have my program in it. My program will be running. So that allows me to bootstrap it from a program, so I don't always have to have a programmer in there. It would kind of suck if every time that you wanted to use your iPhone, you had to plug it into the PC first and flash it with firmware. So before we get into too much about that, though, we'll actually talk about building circuit boards. Sorry, I know I said that I wasn't going to do this, but I didn't really pay attention the last time you did it. How many of you have built a circuit board before? Like a production board? Like you've actually like shipped something off to a manufacturer and said, hey, send me a board file back. Okay. For those of you that haven't, we're going to level set. And again, we'll try to move through this material quickly enough that those of you that have don't just all fall asleep. I want to level set, first of all, on just what a PCB is, right? Fundamentally, it's just a way of connecting components together in meaningful ways. That's it. In the same way that I use a breadboard to connect components together with wires, I'm using a PCB, but I'm actually using copper tracks which spread across a board. Those copper tracks are actually the conductors, which function in the same role that a wire would on a breadboard. So this is actually circuit board. This is what it looks like usually before they actually build your board. Now, this is a reasonably small piece. Typically, manufacturers will have something which is like 18 by 22 inches or 18 by 24 inches. And your board will, at least for some length of time, cohabitate with all these other boards that they're manufacturing at the same time. This is pre-clad with copper. And what they do is either through a process of chemical etch, remove all of the copper that they're not, that you don't necessarily want on the board. This is single-sided. Both of these have basically a layer of copper on top of an insulating layer. Okay? Now, the insulating layer, depending on the board that you're actually building and what machines, what equipment you're going to use, that sort of thing, the insulating layer may actually be made up of different types of material. The typical material is something we call FR4, which is, FR stands for fire retardant, and FR4 is a fiberglass-based material. If you are using a milling machine. And later today, I'll show you guys my other mill, and it's pretty amazing. It's like CNC TV, right? You just stare in the window, you're like, ah, it's doing something. In milling machines, you want to use something called FR1. And the reason you do is because the fiberglass dust from these things, it's really nasty. You don't want it buried deep into your lungs with little bits of fiberglass material in there. So using FR1 is much better to like a paper-based material. That won't produce a dust which is nearly as toxic or noxious for you. I'll pass these around if people want to look at them. I don't know how many people have actually seen them before. So your typical thickness of a printed circuit board is 62 mils. Anybody know why? So it actually came from the thickness of a single sheet of plywood. Total randomness. Yeah. That was it. There was nothing magical about it. It was just that. Drop some components through a sheet of plywood, connect some wires, wire wrap them on the bottom side, and you know, that'll work. It's a good carrier. So 62 mils is actually what we've decided to use. Over the years, we've stuck to that. So pretty much every circuit board that you build will be 62 mils unless you have some reason to change it. When you go to a manufacturer and you say, I want a quick turn prototype, your boards are coming back 62 mils. Okay, 62 mils thick is important in the event that you're going to build something which needs to plug into a PCI connector or something like that, where you've got a friction fit and you've got a limited space where the board has to slot in. So you've got to get that thickness right. There are some specs on that, but it's kind of beyond the scope of what we're going to talk about. This is actually what the routed boards look like. In this case, both of these have been milled out. So you'll see a whole bunch of different copper areas left intact on here. And we'll do this periodically. I mean, we'll add quite frequently, actually. There'll be big, large areas of copper, swaths of copper all over the board, and then the tracks on the board itself. Now, that doesn't look like most circuit boards that you've seen, because most of the circuit boards that you've seen actually have a green coating over the outside of it, or some colored coating outside of it. Here's black. I've got red. The material is called solder mask, and we'll talk about that in a minute. And that's just there to prevent you from shorting a bunch of stuff together and make it easier for you to solder to the board. Both of these have actually been milled out on a milling machine. This board I didn't do. This board I did. You can see my very careful 45 and 90 degree connections. We tend to do that more as convention than we do as a requirement. So when you lay out circuit boards, you don't see a lot of curvy tracks. These sort of non-orthogonal or non-45 type tracks and things like that. It's not terribly common that we do these sorts of tracks like this. Anybody know why we do 45 and 90?
If you have like a 90-degree turn, it'll etch away, like when you're etching away the copper, it'll heat inside of the turn.
It's actually more primitive than that. It used to be that we did all of this stuff with draftsmen who actually cut these things out of tape. And to make sure that we got the clearances right, we didn't have any software that could actually measure the clearances because we were actually doing this on a light table. And so it was actually reasonably easy to maintain the clearances if we just made sure that everything was at 45 and 90 degree angles. Then the distance between the tracks was something that we could maintain. And we would have pretty good success in building something which we could reliably say, oh, well, that's 45 degrees, right? And then that distance is definitely 10 mils from one another. So that's actually it. It's way more primitive than that. So some basic PCB terminology. And again, apologies for those people that have actually built a board before. But for those people that haven't, let's just kind of level set on some basic terminology. So again, I said a circuit board, nothing but a means to connect together components in meaningful ways, right? So here's a component, right? There's a whole series of different components, different types of components that are actually out there on the market that you can use to build all manner of different things. I'll pass around sort of a selection of different parts that you can have a look at. And some of them, well, More frequently, they come on a piece of tape like this, because we do an auto insertion process where we drop the components down on a machine. The machine comes in and optically figures out where the component is, picks it up, figures out its orientation, and then sets it down onto a circuit board. We do that because the volume in which we're building circuit boards is pretty impressive these days. I'm going to pass around kind of a collection of different components. I challenge you to find the components in this strip. Components have gotten considerably smaller than they used to be. Those components, you can't even see the pins on them, but that's actually the part. This component, which we call a ball grid array, has a bunch of pins on it. You can kind of circulate them around. This is a strip of little discrete resistors. This is the ATmega328. This is at the heart of the Arduino. At least I think it is. I didn't look at the part number, but. So there's a whole variety of different components. The idea is that we take a component, we have to create a component, we have to connect it to the circuit board, okay? The components themselves have pins, and they connect to the circuit board by way of pads. We either call them pads, sometimes you'll hear them called lands, because the terminology, the concept of a land, like the landing point where the component lands on the board, it's a land pattern, which is the area that the component lands on the board. Nomenclature it exists. It's fairly common, probably not as common as the term pad. Now, component pins, or leads, you'll hear the term leads all the time, they make contact with the board at some point where I've got copper on the board. So exposed copper on the board, component pin, applying solder to the component pin, and that copper pad will bond the pin to the pad, and then to whatever adjacent track that actually connects it across the circuit board. That creates the connection to those conductors, which will drag the component across the circuit board. So here's a component pin, here's a component pad. This is a track. It actually goes into a through-hole pad or a via. Surface mount pads, we also have through-hole pads. Through-hole pads basically are just that. There's a hole which drops through the board. The hole is plated on the inside, usually, unless you do it on a milling machine. Then it's up to you to plate it. Component pins pass through there, and then you solder the component pins, usually on the opposite side of the board. It used to be that we would do circuit boards with only components on one side. So sometimes you'll hear the top side of the board referred to as the component side and the bottom side referred to as the solder side. That's changed. And it changed with the advent of what we call surface mount components, or components in which the pins, like these gull wing pins here, actually made contact with the surface of the board rather than actually dropping through a hole on the board itself. That enabled us to put components on both sides of the board. Okay? So now, with a much smaller board area, we could actually get more components on the board. These days, so much functionality is actually consolidated into a single component that that's actually becoming less and less of a problem. And you'll see now actually a throwback to people doing boards with only components on one side of it because there's so much functionality wrapped up into a chip. In that one little BGA chip, which is floating around the room, it's called a Raylink chip. You'll see the silk screen on the outside of the chip. That Raylink 5350, which is the BGA that's flying around the room, it's about 7 millimeters by 7 millimeters, or sorry, 10 millimeters by 10 millimeters. That's a Wi-Fi router on chip. So it's got a 4-port Ethernet interface. It can run OpenWRT. I've had Linux running on it with Node.js in a proper configuration with MongoDB on that chip. It's $6. So when I say that, you know, we've done a lot to consolidate these things inside of a chip, that's very much true. And the trend is that if anything looks like it's going to make sense as a module, the semiconductor manufacturers are smart enough to say, well, how can we possibly condense that into a single chip, because that gives us a unique position to be able to sell that functionality, encapsulate that functionality. And you'll see that progressively as time goes on. There's just history of that over and over and over again. So a lot of these IoT modules that you're buying today will eventually be consolidated into a chip, and it'll be like IoT on a chip. Yeah?
Well, what is the chip? What's it called?
And so it's buzzing around the room right now. That one's called the RT5350 by a company called Raylink. Now, Raylink was bought by MTK, well, a company called MediaTek last year. Both of them are Taiwanese companies. But Raylink is at the heart of a lot of these small routers that you find in homes inside of places like China, that sort of thing. So Tenda, which is a very popular home router brand inside of China, is powered by Raylink stuff. Or MTK, MediaTek stuff. So I think the MediaTek version of that chip is now the 7360 or something like that. But if you look for like MTK 7360, or if you look for the Raylink 5350, then you'll see the chip buzzing around the room. It's this small little 10 millimeter by 10 millimeter BGA package. BGA, sorry, just to not throw out terminology and not define it, means ball grid array. We'll deal with that in a minute. Because we could put components on one side of the board, but we wanted connections that potentially could spread to components on the bottom side of the board, we actually have vertical structures which pass through the board that we call vias. So I have a track. The via is basically a drilled hole. Later in a post-process, we plate the hole. So now we create a conductor which moves along the z-axis through the board itself, connecting the top layer of the board to the bottom layer of the board. Okay? If you use something like a CNC machine, that connection isn't made there, because just simply drilling through the board itself doesn't actually plate the hole. So there are all sorts of techniques, some cheekier than others, for how you plate holes. There are some which you can use professional equipment to plate holes, or you can do what I do and snip the pins off of other components and drop them in there and solder them in place, or just fill it with solder or something like that. But fundamentally, you've got components and connections. That's it. Like, that's what we're trying to put together in some meaningful way. So various components, you've got, this is all one part, which is the LM1117. It's a classic, but it's an oldie but a goodie. It's a voltage regulator. Various outputs, takes an input, produces various output. Comes in a whole variety of different packages. Okay? Some of them are through hole. Pins actually go through the board. Some of them are surface mount. This is a collection of various through hole and surface mount components. Ignore my text for a minute. This is surface mount. This is through hole. This is through hole. Okay? This one doesn't look necessarily through hole, and it could be used as surface mount, but this one was actually positioned as a through hole component. So that regulator that we're using, which is on this board here, let me drop this over here for a quick second. So you'll see that I've got this, it's kind of hard to see here. I've got this black regulator, which is right here, which has a little metal frame around the outside of it. This is the back side of it, the thing with the little metal frame that my finger's touching right here. That's actually the regulator. So, and that actually is the LM1117, which is in that type of package. We call it a TO220. It's got a little metal plate usually on the back side of it, and the little metal plate is there so you can attach a heat sink to it. Because one of the ways that this type of regulator regulates a voltage, a higher voltage to a lower voltage, is by dissipating energy in the form of heat. The higher the input to the output, the more heat that it produces, because that's its only way of dissipating energy, right? It's important to kind of understand that in the context of most of these things, that sort of fundamental rule of thermodynamics, the idea that matter can't be created or destroyed sort of thing. I've got to do something with any energy that's going to be moving around the system in some way. That can come back to bite you. So lands, pads, leads, pins. Lands and pads are where component pins make contact with the board. Leads and pins are those things that are actually on the component themselves. Okay? They fall into a couple of different categories. Plated through hole, sometimes you'll see the abbreviation PTH. Sometimes you'll see the abbreviation TH, stands for through hole. And then SMT and SMD for surface mount technology or surface mount device. So these are component pins actually making contact with the pads. It's very hard to see here, but because the contrast isn't great in my image. But there's actually a track which is coming off of each one of these different pads and kind of runs off to the side of the board. True hole pads, this is kind of what the basic structure looks like, okay? I've got a pad which is on the top side of the board, I've got a pad which is on the bottom side of the board, and then I have plating which connects that vertically through the board, okay? The pin drops through that hole, and I solder it on the bottom side of the board, okay? So that's kind of the basic structure for that. It's, you know, it's not terribly scientific, at least not at this stage. I'm sure it was at some point. Here's a bunch of components here. You see component pins. Connecting those things together to the pads actually on the board. These are for surface mount components. These are little vias. This is actually a component here. This is like that component which is running around in those white strips of parts that are buzzing around the room. Now, circuit boards are not just 2 layers. In many cases, they're more than 2 layers. And the way that we do that is we actually layer material together and then we put a thin film of bonding agent in between them to actually connect the layers together. Okay? So we have different layer types, and we're going to talk about the different layer types. Don't worry, we'll get into the software, I promise you, but we got a level set. PCB signal or routing layers, okay? This is, you know, far and away probably the most interesting layers on the board are the layers in which you actually route the connections between components, okay? On a 2-layer board, that would be the top layer and the bottom layer of the board, usually, okay? If you're going to CNC something, you might not necessarily put tracks on the bottom side of the board or connections, traces on the bottom side of the board, only because you have to flip the board over and then actually mill that out, and then you've got to make vertical connections by vias through the board itself. So if you can avoid that, it's great. Under rare circumstances, can you avoid that? History sort of says these days that it's just, it's just a profound waste of time for me to try to get all of my tracks perfect on one side of the board. So I end up using the bottom side all the time. So we've got routing layers. I want to talk a little bit about layer stack-ups on a board, multi-layer boards. So here's actually a 4-layer board, layer by layer, okay? This is a board that's actually sold in the Hackaday store. It's an FPGA board that I sell through Hackaday store. So this is the top side of the board. You'll see the components, you'll see the component pads, you'll see the component pins, and then all of the tracks which are connecting those things together, okay? This is an internal layer of the board. Now, the large copper area here is what we call a plane layer. It's very, very common to use a plane layer. And it's very, very typical for us to do signal layer or routing layer and then plane layer. And then routing layer and plane layer. So this is the bottom side of the board. And the reason why we do that where we have a plane on the opposite side is this, so we never have more than 2 signal layers adjacent to each other, okay? Otherwise, there's just too much risk of noise and crosstalk and all sorts of things like that. It's much better to have a plane layer in there, which helps to somewhat isolate the different signal layers from each other. So I've got a routing layer here, plane layer, routing layer. Now, the way that the layers are actually put together, so this is the top side of the board. You can see the green solder mask on the outside of it. That's actually the copper there. The copper is exposed here because that's actually a component pad. There's a thin layer of material in here, another thin layer of material in here. Both of those are insulating materials, right? So they separate the layers from one another, like the fiberglass in FR4. Okay, the fiberglass in FR4 is what we call a core material. Okay. We also use another type of material called pre-preg. And pre-preg is just a sort of mashup of the words pre-impregnated. And basically what it is a heat-sensitive epoxy material that we can heat up and use it to actually bond layers to one another. Okay? We can also control the height of pre-preg material. That allows us to do some other things when we get into the RF world that are pretty interesting. There are different types of core materials. These days, if you're going to do something which involves wireless, usually we don't. Well, the core material for FR4 is actually pretty inconsistent. It's kind of hard to understand that until we get into some other stuff later on, but there's some inconsistency in it. The inconsistency is related to its ability to function as an insulator, okay? And that subtle inconsistency there has an effect on the performance of things which have a very specific impedance. So we use other types of material. There's something called Rogers, which is slowly but surely kind of creeping its way into more of sort of modern RF system design. But this is actually the typical stack up. I've got top layer copper, a pre-preg material, a plane layer, a core material, a pre-preg material, and then the bottom layer copper, okay? And I've got my two planes in between there, okay? Now, the green stuff that's on the board is what we call solder mask or solder resist. And we put it on top of the board so we don't just short everything together. And I'm going to pass around a couple of circuit boards, and these are milled on a milling machine, and they in turn don't actually have solder mask on them. And you'll see what ends up happening is that solder tends to run all down the tracks. And the risk that you're actually going to short something together is pretty high, okay? So what we do with the solder mask material is we cover up all except for those things that we know we're going to solder to. Everything else is covered in a material. So we apply a mask that applies a material to it that only exposes those things that we know that we're going to solder to. We create a small expansion on that, which allows us to get some solder into that area. So there's a little bit of a swell there where the green material kind of pulls back. But that gives us a nice, easy spot to solder to it without the likelihood that these two things from here to here would necessarily bridge to one another, because there's a material in here which very deliberately resists solder, okay? You'll see here, this is sort of a cross-section of a board. I've got the solder mask material here. The pad is actually exposed. This is a surface mount component. So in that white strip of components that I passed around the room, that's actually this type of component here. It's a discrete resistor or capacitor or whatever. It doesn't matter. But it's got, this is actually the pad, wraps around the edge of that component. That's where the pads, sorry, these are the leads on that. The pads are actually exposed here on the board. This little bump right here is actually solder paste. We'll talk about that in a bit. But I can set the component down on there. It'll solder between those two things. But it shouldn't, because this resists solder very deliberately, again, it shouldn't actually jump from one to the other, okay? Now, typical sort of production circuit boards, rather than doing the old soldering iron, you know, one component at a time, if you look at some of those components that I sent around, you'll realize that they don't have any exposed pins. There's nothing that you could actually solder to from the outside of the component, because the pins are actually underneath the part. We address that with using hot air. So we, instead of using a soldering iron and touching the board, we actually just heat up the board with hot air, or with a plate that we call a reflow, that we use in a process called reflow, where we heat up the board itself, and then the solder becomes viscous and it actually bonds to the pads. That allows us to solder components which have pads that are exposed, or that aren't exposed, to actually make contact with the pins on the bottom side of the component. So this board here, on the top side of the board, the one with the big square on it, for those of you in the back of the room, it's like, yeah, whatever. So on the side with the skull, not very interesting, but if you flip it over to the side without the skull, there's a component called a BGA package. That's actually one of that railing chip that I sent around the room. It's a BGA package. And you can see the pins exposed there, but they're just on the bottom side of the actual part itself. So the only way to really solder to those things is to either apply solder to it, set the component on top of it, and heat it with hot air, or heat it up on some sort of a plate which will distribute heat evenly after you've applied solder to the board. The solder material that we use most commonly today in automated assembly is something called solder paste, okay? And solder paste is actually made up of a combination of solder and flux. And it comes either in big buckets, if you're doing lots of circuit boards, or it comes in little syringes. And the solder paste, just to give you a sense of, here's a stencil. This is actually a solder paste stencil. And I'm going to pass around these green boards and the solder paste stencil. And basically what we do is with the stencil, you can see the little holes there, we apply the stencil over the top of the board, we apply a layer of paste, We squeegee the paste across that. The thickness of the stencil controls the height of the actual paste that we leave behind. We remove the stencil, set the components down, and then we heat the whole thing up. The paste is a paste because it's a combination of solder and flux. So what we do is we grind the silver material into a dust, mix it with flux. That creates something which is a paste. Apply the components to it, and then we heat it up, and then components bond with the board. So this is actually a solder paste stencil, which is for this green board. And you can kind of take a look at it. So there's two layers there. There's the top side and the bottom side. This one is actually a stencil for the same board, but there's multiple instances of it. That's because when we build a board in automated assembly, we actually build multiple at the same time. So it's easier for us to put a bunch of boards on one of those big 18 by 24 panels, then go through and actually route all of the boards out later using a milling machine that can actually route out the boards themselves. So this is a solder paste stencil. I've got the paste floating around. This is actually the squeegee which came with that stencil that I have there. It's basically just a metal foil. Usually solder paste stencils will come in much larger pieces. The one that's there is just nice and sort of convenient, pocket-sized, I guess, for everything that I wanted to show off today. And then the other layer that we have on the board is silkscreen. And the silkscreen is all of that cool white text or black text or green text or whatever. And you can get silkscreen in different colors. I would discourage you from getting too clever with the colors. I've seen circuit boards that just look horrible because their color scheme was terrible. It was just like, oh, well, you did white text on a yellow board. That really looks bad. I'm sure that was interesting in 1978. Like, gold. I didn't know that you could do that color. There is always somebody who's just too clever with silkscreen. And it's inevitably the circumstance in which it's going to come back, it's going to go to a repair department, somebody's going to pull the component off, and they're going to find your rude finger buried underneath the component that you embedded in there 2 days before you quit and went to work for that other company. Good silkscreen, though, can make it really, really easy to solder stuff onto a board. So I would really encourage you to use good silkscreen on a board and use text on a board in meaningful ways. There are some things that are completely absurd, okay? I don't need to know the part number on the board itself. I need some unique designation that helps to sort of disambiguate, right? So we use what we call reference designators for that. We call components C1, C2, C3, C4 for capacitors, right? R1, R2, R3, R4, U1, U2, U3. That IC thing, that's like a weird European thing. Don't use that. That's stupid. The silkscreen on the board, though, is super useful, particularly if you're going to hand solder something. I love this piece of text here. It's hard to read from the back of the room. It says, if you can read this, you forgot the heat sinks. That's a good piece of text, right? Like, I think that's Ian Linné from Dangerous Prototypes who did that board. It's a good board. Arduino has some interesting mix of both good and bad silkscreen. I don't like the fact that they don't actually label any of the parts based on reference designator on the board. So there's nothing telling me that this is U1 and U1 happens to be that part. So when I'm looking at the schematic, because the schematic is my map, that's my guidebook, right? When I'm looking at the schematic, which shows me the part number, there's nothing to equate this part with that part in schematic, okay? This use of silkscreen over here, obviously everybody depends on that. That's good silkscreen, right? There are all sorts of things hidden in silkscreen on components on board, or under components on boards, I promise you. It used to be a lot more popular to do that sort of thing. We've kind of all grown up since then. Well, some of us. So far, we've got the signal layers, routing layers, right? We've got a solder mask layer. We've got solder paste. We've got silk screen, okay? We'll talk briefly about just kind of the workflow and how those different layers actually fit into the assembly and fabrication workflow. There is a difference between fabrication and assembly, Okay? We tend to use the term assembly when we talk about putting components on the board. We use fabrication when we talk about the creation of the bare board. And you'll hear the term manufacturing, which is sort of an umbrella term that talks about both of those processes. Okay? If you go to somebody and say, I want you to assemble me these boards, they will look at you and say, but I'm not an assembly shop, if what they do is make bare boards. If you say, I want you to fabricate a bunch of bare boards, they'll understand that, right? They'll probably slack you on it, but they'll know that you're total bush league, and they'll take advantage of you in horrible ways. So assembly, pick and place, and reflow. All of these things tie into the process of actually getting components on the board. So if we look at the layer construction of the board, we put parts on, we go ahead and we route a board, we draw all of our meaningful connections in our CAD tool, that sort of thing. We get a bare board fabricated. When we put components on the board, this is kind of the workflow. So for production soldering, usually what happens is we screen print the solder paste. So we use that stencil, apply the stencil, screen print the solder paste. We set all of the top layer components on the board. Okay? We then go through and reflow the board. And by reflow, what I mean is we put it through an oven at a very steady temperature that causes everything to heat up. The solder becomes viscous. It bonds with the pads. There's a genius effect that happens when you're putting components on a board called surface tension. Surface tension is your best friend. Surface tension will actually cause component pads to shift a little bit, or component pins to actually shift a little bit if the component isn't perfectly centered on the pads on the board, which actually makes it easy for you to make those connections. When the solder heats up, it actually kind of draws the component right onto the pads because metal on metal will actually pull itself, will actually cause it to kind of pull in the direction of where it needs to be. So when we heat up the board through reflow, even if the component isn't perfectly centered, it'll actually center itself through the process of heating it up. Okay? That's genius because it totally saves you, especially if you're going to do hand soldering of stuff too. And by hand soldering, I mean if you're going to use hot air. You can reflow almost anything just using hot air. Okay? There's very few parts that I can't do by hand, but it takes work. It takes time. It takes practice, right? BGA parts I can do by hand with just a hot air pencil. Okay? I heat it up, and the great thing about it is that the component will actually kind of naturally gravitate towards where it needs to be because the surface tension of metal on metal will draw those two things together. Then what we do is we screen print the solder paste on the bottom side of the board, place the other surface mount components, insert through-hole components, and then go ahead and heat up the board again. Now, the obvious question in this is, well, why don't all those components just fall off the board when you heat it up again? And there's kind of two answers to that. One is that surface tension will just cause them to actually stay in place. The other is that if it was really a problem, you could just have solder which actually operates at a much higher or a much lower temperature. And that would allow these components in the second half of this process to be applied. Well, if these components in the first half of the process, they never get to a point in which the solder becomes viscous and then they just fall off. It tends not to happen, okay? In terms of, so this is just anecdotal. If you're going to get 5 boards built, 10 boards built, 50 boards built, something like that, particularly if you're going to do it through a quick turn place in China, hand assembly is actually less expensive than it is to actually go through automated assembly. Automated assembly is a really painful process if you're not going to do at least a few hundred pieces, because to set up a machine could actually take somebody all day. Okay, so you're paying a machine operator to spend the entire day putting reels on a component or on a machine to then go through and actually populate your board with components. Okay, to set all of that up, feed all of the tapes the right way, get your trays in there, tubes, because components come in a variety of different forms. This is a tube of components. Okay, and you can imagine at some point somebody's got to open this up and actually feed it into a machine. And the machine's got to know how to pick up that component, drop it into the board, and then heat it up and actually cause the solder to connect to the component pins, that sort of thing. If there's 50 boards to do, hand assembly could be considerably cheaper. The thing that I've noted since coming back to the US is that hand assembly in the US is not necessarily that way. So hand assembly in the US can actually cost you quite a bit, largely because we don't have the same manufacturing expertise as what people do in assembly shops in China. It just doesn't exist here. Unfortunate, but true. There's another soldering technique. We don't really use it anymore, but the reason I bring it up is because there are circumstances in which you will see components that have a little tag on them that say that it was designed for wave soldering. The idea with wave soldering is that you would align components on the board with their leads facing in one direction, okay? All of the component pins facing in one direction. You would run it through a wave of molten solder. It would sort of pass over the components, and the solder wouldn't stick to anything except for the exposed metal area, which would be the pins and the pads that were actually on the board. We don't use that technique anymore. But you will see, particularly if you use Eagle, in the Eagle libraries, that there are some libraries which indicate that this is one version of the component and then another version -W or something like that, which is an indication that it was designed for wave soldering. Usually that relates to the orientation of the component, because for wave soldering, the boards have to go through where their leads are facing in one direction, okay? Now, with current components on circuit boards, that kind of doesn't jive anymore, because we've got BGA packages and QFN packages and all these other sorts of things. So it kind of all breaks down at that point. Now, okay. Any questions up until this point? I should pause for a second. Yeah.
At what temperature are you reflowing the board?
It's kind of tricky because different components will actually have different requirements for that. Manufacturers will actually look at that, or assemblers will actually look at it. It could depend. I mean, you could be a few hundred degrees C, you could be probably not much further north of that, because a lot of the material that you're using is already pretty viscous and pretty reactive, in that you've got a pretty substantial combination of flux and solder in there, but it's a good mixture of flux, so it starts to turn liquid very quickly. Solder paste has a much lower temperature than solder from a soldering iron, okay? So soldering irons, you could be up into 400 degrees, something like that, where with solder paste you could be considerably lower than that, okay? I can show you, I'll show you a little bit later today, actually, a couple of tubes of solder paste, and different ones will have different temperature profiles. You can actually see the different temperature profiles on it. So reflow is tied into the temperature profile of the material that you're going to use, the solder material that you're actually going to use.
Specifically along the paste or on the
Yeah. So even the same brand, but different variations will have different temperatures, different temperature parameters on it. So, in terms of picking one versus the other, if you're not doing large-scale manufacturing, sort of 6 of one, half dozen of the other, the things that I would stay away from are things that are designed specifically just for rework. There's something called Chip Quick, which is great, but it's really designed for rework, and that'll have a very low temperature where it actually becomes liquid, and that's actually designed to help you take components off of a board, right? So I'll show you some of that actually a little bit later on today. Yeah.
Yeah, so you're saying that in some cases, like a board will be made with one process, or you might actually have several processes where you can the solder iron the first part, and then the components reflow. Is that what you're saying?
Yeah. Well, so if I'm doing hand assembly on something, it's usually a mix of that. So I'll use a soldering iron for probably, well, I'll use a soldering iron for anything which is through hole. I don't reflow anything which is through hole by hand. And then I'll use reflow only for those things in which the leads aren't exposed. If the leads are exposed, I tend to use an iron. And the irons that I use, and if you come tomorrow, you'll actually see them, I use a very specific type of tip. I use a very sharp chisel tip. And I got that tip actually from, well, not that tip, though it was a tip. It was the tip from my technician in China who said, listen, Chief, if you buy these tips, you can use them to do kind of everything. Just buy those tips. And I mean, these guys do amazing stuff. super, super small, crazy stuff. And I mean, things that like I can't even see, right? Most of the stuff I can do, the things that I have really hard time with are very small resistors and capacitors, because just getting a hold of them is actually very difficult. If it's not really, really small, like that white strip that I sent around with the 603s in it or 402s in it, which are the various sizes. If it's not very, very small like those, then I tend to just use an iron. Those I've started to kind of, well, you can't do it really well with hot air because they blow away. And I've had whole heaps of them just disappear on me, like just vaporize. Actually, it was crazy. My mag connector yesterday, that little black component that I sent around is a really small one. It's like 3 millimeters by 3 millimeters. That was actually stuck inside of my mag connector on my laptop, on my MacBook, because it was in my backpack, and that component just came loose somewhere from one of my boxes of stuff. And that was stuck in my mag connector, and I'm like, wow, I wonder what that's actually doing. Like, I wonder if there's like, you know, is there a way that I can, like, one day I'm going to bump into it and it's going to like be doing something functionally interesting, or not. Yeah. Anyway.
So does it get to a point where even the technicians are so small that they can't do it and they have to release robots?
You know, my technicians can nail it. The ones that I use in China can nail it, but there are limits. So my technicians in China can do 0201, which are generally the smallest of the surface mount resistor and capacitor packages of any consequence. People will use smaller ones, but well, people have been known to use smaller ones, but it's so few and far between. And even 0201s are not very common. 0402, which is that white strip that I sent around, imagine half that size is actually what they're able to solder. And they do it by using the chisel tip, and on the edge of the chisel tip, they actually grab the component lengthwise. So they have both pads. The component is actually basically pad, and then a body of it. They grab it with the chisel tip lengthwise this way, heat up both pads, and then just very carefully set it down on top of both pads, heat both pads at the same time, and the component just sticks. And it's genius to watch. I wish I could do it like that. And I can't, because they just blow away on me. They vaporize. I'm just, yeah, I don't know.
So you just discussed a lot of the nuances and, you know, design space sort of stuff, what temperature solder to use, and you know, different methodologies for sticking your components down on boards. How much of that stuff is manufacturing engineering, and how much of it would we have to deal with if, you know, we design some little board and go send out for somebody to build 25 of them or something? Right. So how much of it is like I would say if you're right. So I would say that if you're going to use a manufacturer, right, you're going to pay somebody else to do this work for you. They'll have all of that information. The only circumstance in which you need to interject is where you have a very specific requirement. Otherwise, they'll know exactly what they need. There are some things which you'll encounter when you get onto their websites, and I'll try to show that later on today, which is actually the goal of this, was to kind of get you to the point in which when you were looking on their website, you're going to be handed all of this information that you need to somehow figure out what information to enter. When you're looking at that information, there's a fairly limited set of options, but they're important, and they come back to you, and you're defining it for them. And part of that, what they'll do on their web page is have the standard model already pre-populated, and then you'll come in and say, well, actually, I don't want that finish. I want this finish. Or actually, you know, I don't want this type of, you know, I want immersion gold as opposed to this other thing, right? And those sorts of variations, that sort of nuance, usually means that you know what you're looking for. Otherwise, under most circumstances, like if you're just building simple microprocessor boards, or if you're even sophisticated stuff, reasonably sophisticated stuff, you won't find that you need to spend a lot of time kind of thinking about it, because they'll deal with it. If there are specific requirements, like, you know, and this is becoming increasingly more common, particularly for software engineers who want to move into the hardware space, but are saying, hey, but I want something that can run Linux. Right? Well, Linux is a big operating system. It's, you know, there's some overhead to it. And if you want to run like proper Linux on something, then you probably want reasonably fast memory, which is
DDR memory, which has all sorts of crazy constraints and requirements. When you start to get into spaces like impedance, the world becomes quite difficult. Well, quite a bit more complicated, I should say. And that's actually the focus of the next probably 30 minutes. I'll actually walk you through some things. And then maybe circle back with me and let's kind of riff a little bit about whether or not in the next 30 minutes or so I kind of answer some of those things for you too.
Do they have big parts and then you can miniaturize the boards so in other words you can't do the small stuff but you can prototype in like say.
Yeah, so well, like that choice of that LM1117, which is that tube that I just sent around, that comes in a part which is 3 millimeters by 3 millimeters. But I chose not to use the 3 millimeter by 3 millimeter version because as a way of introducing people to how to solder things, it's kind of unrealistic to say, oh yeah, and by the way, you need to solder like somebody who's been doing it for 20 years, right? So in a way, yes. Well, first of all, yes. In answer to your question, yes. And there are lots of components which are much bigger. I would never use through-hole resistors in anything that I do. But I use them on this board because it's the kind of thing in which it's good to kind of get familiar with stuff, to understand the relationship between solder and flux and where to apply the tip and where to apply the solder and how to get the right sort of bond and what it should look like and all of those other sorts of things. Those fundamentals, those sort of foundations are really important. And the only way that you get there is to kind of go each step along the way until you get to the point of miniaturization. I will say that prototype and production boards, if you're going to do anything which is truly manufactured, your prototype and your production board should be exactly the same. Because your prototype is actually a way of demonstrating whether or not this thing is going to work under that configuration. So when I build a true prototype, like a pre-production prototype, it is exactly the same as what I'm going to produce. All of the same component sizes, all of the same everything. Because I don't want any variation on that. Any variation is potentially a way for me to introduce some sort of issue in that. And if the next step is to build 10,000 of them, that's potentially catastrophic, right? Once you get the components on the board, it's very hard to take them off and reuse them. It can be done, but it sucks. And so you really want to get things right the first time out. So you build maybe some larger component things, like if you're just building stuff at home. But if you're going to do something which is actually intended to be a product at some point, that's why I say hand assembly is really nice by professional people, because you can give it to somebody who does have 20 years of experience and say, make me one of those. And then you don't have to think about it. It doesn't come down to your soldering skills.
So basically you send that prototype out and design specs to somebody who can make those miniaturized connections.
Yeah.
And then
Get it back and then actually prove that that works. Because my prototypes are really an indication of whether or not I have a viable product. You know? Yeah. We may. I actually have to look. Yeah, actually there's a couple in the office over there. I'll bring a couple over. Yeah. Yeah, no problem. Yeah.
How do you position forward externally on that circuit board
Mm-hmm.
for soldering?
Oh, how do I position it for soldering?
Hold it.
Oh, to actually hold it in place?
How do you position the actual component and hold it in position for soldering?
Yeah. So, well, it depends on the part. So sometimes you use, actually there are little suction tools which you can use that have a little silicon end on them. So imagine a regular suction cup, right? But a suction cup with a silicon end so it doesn't respond to heat in the same way. And then you can actually use that to pick up a component and sort of hold it in place. Other times you can just use tweezers. If you're using solder paste, the good thing about paste is that it actually kind of holds things in place. Otherwise, sometimes I just set them down, which doesn't sound terribly scientific, but I literally go through and pre-dope pads. So what I'll do is instead of soldering to the leads, especially if the leads are all underneath the component, I'll go through and apply solder to the pads, set the component on top of it, hold it maybe with a tweezers, and then just heat it with hot air. But it is amazing how much heat one human finger can take. There's been more than one set of circumstances where I've sat there and like, I think I can just move it a little bit while it's still hot. All right. So all of that other stuff, that's easy. This is when it starts to get interesting, okay? Building circuit boards is not as straightforward, perhaps, as we'd like to hope. There are circumstances in which building a circuit board can be much more complex. The aim of this next little part here is just to kind of help demystify some of the things that you'll hear from people, like, oh, you want to keep your tracks narrow or wide, or keep them short, or keep your components this close to each other or that far from each other, or you want your pads to be this big, or your blah, 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 blah. There's all sorts of different kind of opinions on these things, many of which come down to one fundamental thing, and that's that the board is actually a part of the circuit, okay? Those pre-clad copper boards that I sent out, that I circulated around the room, I've got copper and copper separated by an insulator. That's a capacitor. There's a dielectric value of the insulator, okay? The dielectric value of the insulator corresponds to its insulating sort of effect. That has a direct relationship to the capacitance of that thing, okay? Anybody who tells you that the board isn't part of the circuit is lying, okay? Or full of it. I was going to say something a lot harsher than that. The board is very much a part of the circuit. The question is at what point does it have an effect on the circuit? So if I introduce a little bit of capacitance to the circuit, does it actually change the way that the circuit is going to behave? If I introduce a little bit of inductance to the circuit, is it going to change the way that the circuit behaves? The beauty about most digital electronics is that you're dealing with a very clear window in which you've got a high value, which is above some threshold, and a low value, which is below some threshold. And that's awesome. But the real world is not digital. The real world is analog. And in the analog world, you're concerned with values across the whole range, okay? You're concerned with that middle band. Any variation in that middle band means that, well, is the smoke concentration really high enough for the smoke alarm to go off? So, rule number one, the board is part of the circuit, okay? It's just like any other component. It's very difficult, though, to quantify its effects without understanding some fundamentals of electronics. This image is a great image. I stole this from John Andrezzoni, I think it's Andrezzoni, from Analog Devices. And then I captioned it for him. So when you look at that book, which is like, you know, Getting Started with Op Amps, something like that, Forrest Mims III, that's what he tells you to build, right? But that's how the real world actually behaves. Every pad has an inductance, it has a capacitance. When do I care, right? Every track has some sort of inductance. There are sort of four fundamental elements that you can probably get by with. Yes, you could go back to Maxwell's equations and retreat into a bunch of really complex mathematics, but the truth is that you can kind of distill a lot of these things down to just four fundamental elements. And we use this for 2D field solvers. Field solvers are a way to sort of quantify how a board is going to behave by looking at the relationship of fields. But basically, resistance, capacitance, inductance, and conductance. We call them the RLGC model. Okay? We use this with 2D field solvers where we want to solve for how the board is going to behave. Imagine a simulator that can say, and that's how that track is going to behave. That's what a field solver is intended to do in that context. But this is the real world's cruel joke. Now, it doesn't become important until you get into a circumstance like, hey, I want to build a radio that has BLE, right? Well, okay. Bluetooth is kind of complicated. Radios are kind of complicated, right? There's a lot of stuff in there that you have to think about because circuits are reactive. You introduce inductance, you introduce capacitance, and they behave very differently. Now, I don't want to make this a lesson in Ohm's law or sort of first principles necessarily, but I will take you through some fundamental things because I think just understanding them helps you to understand or develop some sort of intuition or some sort of intuition for how things are going to behave and why we say the things we do. First of all, copper is not a superconductor, okay? PCB traces, they have a resistance, an impedance, an inductance. Pins and pads have capacitance and impedances. We've got vias, which are inductive, they're capacitive. We've got these vertical connections through a board. So you've got this long tube of copper material where you've got, electric current passing through it. I mean, it's pretty gnarly what can actually happen in that context. Coupling occurs between tracks. The notion of crosstalk we kind of refer to in the PCB space more as coupling, where I've got two tracks next to each other that are potentially very noisy, that could impinge on each other, and the signals could kind of get out of whack. A lot of this stuff doesn't happen in low-speed microprocessor circuits. So 90% of the stuff that you're going to do, this isn't going to matter, okay? But it does matter if you say, I want to build wearables and it's going to have BLE. Oh, okay, well, that's pretty trendy right now, and all this stuff matters, at least to some extent. If you say, I want to build an IoT platform, okay, well, that kind of matters. The nice thing about the ESP board is that they've kind of figured out those things for you. So what you do instead is leverage somebody else's module and implement that on your board. Now, they've passed FCC. That doesn't mean that your product will necessarily pass FCC. Just because they passed FCC, if you build a product using something which has passed FCC, the FCC certification doesn't extend to your product. It only kind of extends to your product. You still need to get something certified because you still need to prove that this thing, which includes this radio, isn't actually going to generate any sort of crazy noise that's going to mess up everything that's going on around you. Noise propagates along signal paths. It propagates along ground planes. Amplifiers amplify, and they amplify everything sometimes, so you've got to be very careful to filter things. Digital signals are noisy. Here's the point. I'm going to show you a bunch of stuff. It's going to look like gritty bits. How many people here have done advanced mathematics beyond Calc 1? Okay. God, I should take all of you guys up to San Francisco. Because the crowd in San Francisco was like, yeah, no. But I don't want you to look deeply into these equations. Okay? Just look at what it's actually telling you, right? So if you look at a simple equation for sheet resistance, which has some area, right? It's got a width, it's got a length, it's got a thickness, right? Resistance corresponds to the x and y size of that thing, right? So as the x and y get bigger, the resistance goes down, okay? Numerator, denominator kind of thing. Yeah. Basic high school algebra, right? I don't even know if that's algebra. It's like arithmetic. I was having a conversation with my accountant. My wife and my accountant are sitting together, and we're having this conversation. And the accountant's like, "Yeah, I do math too." I'm like, "No, what you do is arithmetic. I do math." Yeah. No. I wish I did though, because after I paid him everything that I paid him, I don't know who's one up on the other. So as your conductor length increases, your resistance is going to go up. Okay? As your conductor length decreases, then the inverse is true. So some pretty fundamental things here. Your Y value, which is in this case the thickness of the actual copper, as that increases, your resistance is going to go down, right? So the thicker the copper, and you can on a circuit board actually request different thicknesses of copper. We tend to measure thicknesses in ounce values, which doesn't probably mean a lot to most people, but it actually translates to 1 ounce per square foot. So we spread it pretty thin. It's like 1.2 mils or something like that in terms of its thickness. It's 1 ounce copper. Usually, the top and bottom layers of the board are 1 ounce copper. Internal layers tend to be ½ ounce copper. You can increase those values, but I can tell you that there is a point where that doesn't necessarily translate to some of the things that you care about, like impedance, in a big and meaningful way. Okay? Parallel plate capacitor, if you just think about tracks on opposite layers from one another, okay? Think about it for a second, but as the copper area increases, so does the capacitance. Okay? The larger the two plates get, the greater the capacitance. Oh, okay, meaningful, right? you think about this in the PCB context, it starts to emerge, oh, okay, well, there might be circumstances under which I care about these things, okay? As the relative dielectric, and the relative dielectric is the dielectric value, or the value that we use to enumerate that material, that insulating material between those two plates. As that value, we call it the dielectric value, as the relative dielectric increases, so does the capacitance, okay? As the distance between the features increases, the capacitance decreases, okay? Now let me explain why we care about any of these things. Capacitance and inductance, particularly, are at the heart of the formula that we use to calculate impedance. When you build anything which has a radio in it, impedance is incredibly important. When you build anything which has DDR memory, impedance is incredibly important. We will specify on data sheets for memory devices or on data sheets for wireless transceivers. You want something to have a specific impedance. 50 ohms is usually the sweet spot. And what that means is that I need to control the width and the length, the thickness of the copper, and the distance to the plane, okay, as a way of controlling the capacitance and the inductance to dial in the impedance to 50 ohms, okay? And the reason we do that is because if the impedance is matched between the component pin and the adjacent conductor and the antenna that it's connected to, or the memory that it's connected to, or something like that, then the full signal propagates from one point to another. If it doesn't propagate from one point to another, if the impedance is different, then we get what's called a reflection. And some aspect of that signal actually reflects back onto the adjacent conductor, okay? So we match these impedances by controlling these inductances and these capacitances. So when we pick a trace width, we pick a thickness of the layers on the board, a height of the layers on the board, or a thickness of a copper or something like that, all of that stuff will affect those things. So a couple of examples where you care about it. BLE, Wi-Fi, okay? Anything that's wireless, you care about it. DDR memory. If you want something which has large memory capacity, there's only one solution, and it's DDR memory, and it's complex. DDR memory has some crazy specifications for it, particularly DDR3. DDR1 was reasonably easy. DDR2 got much more sophisticated, much harder, because the performance is much better. It's just that much faster, okay? And memory capacity is greater. You got to DDR3, now you've got much, much greater memory capacity. You've got much, much better performance. Now we're going into DDR4, and that's insane, okay? So all of those things are impedance controlled. Impedance control, anytime you hear the term impedance, you should be thinking capacitance, inductance. You should be thinking about the circuit board and the structure of the board itself. The board is what is going to make those things achievable, okay? And your choice of components in that is also pretty important. Sorry. As far as inductance is concerned, as the length increases, so does the inductance. As the width increases, the inductance decreases. As the height increases, the inductance decreases. As a frequency of a circuit changes beyond a certain threshold, so if I have things which are switching very, very quickly, as soon as I start to get up into gigahertz ranges, something like that, inductance actually changes, because what happens is something we call skin effect. And without going into a whole bunch of detail with it, with the skin effect, essentially the electrons start to pool to the outer edges of the conductor. They concentrate on the outer edges of the conductor. So now I've got most of the electrons on the outer edges of the conductor. The center part of the conductor, the electron distribution is no longer even along the length of the conductor, and I've got now this thing with all of the electrical energy sort of pooled around the outside of it, this physical conductor like this, which tends to behave very much like an inductor, and the inductance changes pretty dramatically. Anyway, via inductance, there's a formula for it, but the point is that as the z-axis, length of a via increases, so does the inductance, same as what we talked about with the track. And as the diameter decreases, the inductance increases, okay? Via capacitance, okay? I've got a ring around the outside here. I've got plating which runs through it. The wider the ring, what we call the annular ring, or annulus, the lower the capacitance. The greater the distance between the pad and the plane, the lower the capacitance. And as the via height increases, so does the capacitance. Okay? These are the trace impedance formulas. And the thing that's kind of unfortunate in these is that there's a lot of stuff which is kind of hidden behind these that you don't actually get to see. These are formulas that you use to calculate impedance depending on layer stack up, whether it's a track with an adjacent plane, whether it's a track inside the board with an adjacent plane, whether it's a track nested between two different planes, different configurations. So microstrip, strip line, embedded microstrip, that sort of thing. It's beyond the scope of everything that we're going to talk about here to go into much detail in it. But the thing that I would emphasize is the fact that if you start to explore those places, come back to this slide deck and then start to ask the question, you know, do I really know how this is going to behave? Do I really have an understanding of how this is going to behave? And is this the kind of thing in which I need to care? And if you don't have an answer to that question, either jump up on a forum or you can shoot me an email. I'm happy to try to answer it for you. Here's a standard board construction from one of the manufacturers. And that standard board construction, if you look at the relationship, this is actually a microstrip, which is what we use in wireless, one of the things that we tend to use in characterizing transmission lines, not just wireless, but transmission lines in general. This is actually the construction parameters from Sunstone circuits. Sunstone are the guys that did these little green boards that I passed around the room. These are the construction parameters, and what they will tell you is, here's the thickness of the copper, here's our tolerance. Here's the thickness of the bonding ply, and here's the tolerance. Here's the thickness of that internal layer, here's the tolerance, blah, 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 blah. If I want to understand, hey, I need something which is at 50 ohms, impedance, I'm going to plug those things in here. I'm going to find a calculator on the web, and if you just type impedance calculator, you'll get like 2.5 billion results. The values that I'm going to plug in are going to come from the manufacturer's webpage, and if those aren't suitable, then I'm going to go back to the manufacturer and say, hey, this is what I need. What parameters can I vary to get to that thing? Okay? Different fabricators will have very specific things that they look for in their page where you're plugging in your information, but almost all of them will have a drop-down that says, do you have any controlled impedance tracks? You say yes, and they're going to say, oh, okay, which one is it, right? Point it out to them. They love information, okay? So, developing some rules of thumb, and don't freak out, okay? Power distribution and grounding is one of the bigger problems on a board, okay? How we actually get connections, how we get the power system connected. And part of the reason for that is that that's like the single most popular series of connections on boards. Everything is connected into the power network. So if there's a bunch of noise on the ground, or if there's a bunch of noise on power, it's going to propagate through to every component. And the right power distribution and grounding scheme can actually help to make a board work that otherwise might be problematic. So, power distribution networks. Power lines should always be kept to the lowest possible impedance. By impedance, if we talk about the relationship between inductance and capacitance, and we know that both of those things are directly related to the area of copper, ergo we try to do larger tracks for power connections. Well, what's a large track? 20 mils? 30 mils? You can carry an amp of current through a 10 mil track, okay? But what we're actually trying to achieve is a very low impedance. We want power to respond very, very quickly. We want power to be well distributed throughout the board. So we'll look at power lines and try to keep them to whatever their lowest possible impedance is. Greater width, lower impedance. Thicker copper, lower impedance. So thicker copper, if you've got a high power board, if you're going to switch mains power, right? 220 volt, 10 amp, or 120 volt, 10 amp, something like that. You've got a lot of power going through there, right? If you want to switch on and off that thing, whatever it is, and I don't know, it could be some purely resistive thing like a lamp, right? It's got 100 watts going to a lamp or something like that. If you want to switch that thing on and off, it's quite a bit of power, right? So you actually want to be able to control whatever the track width is going to be. These are some different power distribution schemes, and I'm not going to belabor them too much. The idea here is that to avoid noise, This is actually the preferred layout. And the preferred layout really comes back to trying to make sure that each individual component had its own power connection and its own return. It's not so practical. Okay? Reality is it's not so practical. This is acceptable, kind of do these sort of large distribution schemes. And in this case, this larger sort of distribution here could easily be handled by a plane. So typically what we do on a circuit board, which is more than 2 layers, is top layer signal, bottom layer signal, a ground plane, and maybe a power plane. Okay? On a board that's 2 layers, oftentimes you'll see people do a large polygon area, either on the top of the board or on the bottom of the board, which is a ground, right? To provide a very quick return so all of the noise isn't propagating along a large ground track all the way through. Everything that goes into a component has to eventually return, right? I mean, this is, Miss Mabel's Science Class 101, right? You close a switch and, the circuit creates a closed loop, and it's got to go in and it's got to come out, right? So in those cases, we want to make the return path as short as possible, so none of the noise actually propagates through the system. To make the return path as short as possible, by return path we mean ground, to make that return path as short as possible, we draw a track, drop a via, and connect it to a plane. That's the easiest, safest way to do these things. So how do you actually pick a track width? Well, there's a lot of different ways. If you're going to do something which is power oriented, that sort of thing, the first thing that you should be looking at is how much current do you actually need to carry. Okay? Current and voltage, that'll equate to power. IPC, the Institute for Printed Circuits. If you don't know IPC, familiarize yourself a bit with them. So IPC writes a series of standards, series of specs, probably too many specs. A lot of them could be consolidated, but I guess they got to make money too. But they write a series of specs that include things like how to pick a track width based on current carrying capacity on a PCB. So IPC 2221, which was the previous formula, this year or last year maybe, they modified the formula so it was no longer a formula, because once the formula gets out on the web, then everybody knows about it. Now it's all tables, so you actually have to buy the spec to actually read the tables. It's kind of a snarky little cheeky thing to do, but anyway. The original formula, which has held for 25 years, basically gives you a sense of, hey, this is the current that you want to carry in amps, and this is the width for 1 ounce copper. This is the width for 2 ounce copper. Okay? It's just pretty linear. Okay? So if you really want to know how to do the formula, you can do it. This is the formula for K. There are some good calculators on the web. Just look up IPC. How do you actually route it for power? The sweet spot is probably 20 mils on most boards for a power connection, for a power track. You start to go too small, it becomes problematic. You start to go too big, it just looks clumsy. There's nothing probably wrong with you doing a 30 mil power track, but the reality is that you have so much capacity to carry current with that, you're kind of overdoing it. You're just creating a lower impedance, which isn't bad, don't get me wrong. So power supply clearances. IPC has a spec for power supply clearances. And the only reason why I throw this up here is because I don't want you to use this spec. Because this has to do with arcing. And power is actually leaping between these different things. And their spec is all built around these things actually arcing to one another. And I looked at it and I was like, okay, yeah, that's ridiculous. Generally, if the spacing between things is a function of the width of those things, you're probably pretty safe. So 20 mil track, 20 mil spacing. 30 mil track, 30 mil spacing. Do you really need 30 mil spacing? Probably not. Can you do 10 mil spacing? Yeah, for the most part you can. If you have some analog stuff, some digital stuff, you always isolate analog from digital. So if I've got some analog sensor, some analog front end, because I want to be able to sense something in the real world, the analog front end needs to be well isolated from the digital side of the circuit, because digital parts of the circuit generate all sorts of noise. They're noise immune because they live in that range where they've got that whole threshold above which it's a 1 and below which it's a 0, which is exactly the reason why you should never buy the high-cost HDMI cable, Because the reality is that it's digital. The data's either there or it's not. Like there's not really a lot of loss going on in there. Maybe along the length of the cable, but digital signals are pretty noisy. So you want to keep them away from analog signals. We isolate analog from digital. We route analog sections or digital sections around one another. We never actually plug the digital underneath it and say, well, I'll put that on the bottom side of the board. The bottom side of the board is not an acceptable escape for, hey, this thing is now isolated from this. It doesn't work like that. In most cases, it won't work like that. Unless you're doing something like a 4-layer board where you have a ground plane in between there. Okay? So digital signals, generally speaking, in terms of digital track widths, on most boards, 10 mil tracks, 10 mil spacing, score. You're good, right? Can you go smaller than that? Oh, hell yeah. I mean, I do usually 5 mil tracks and 5 mil spacing. I can't do them on a milling machine, though. And if you do something like chemical etch, like how many people have ever etched their own PCB? That's all the older people in the crowd, too. Like, oh, yeah, I remember buying that ferric chloride stuff. Glad I don't live in that house anymore. So if you've ever etched, and I lump myself into that group. If you've ever etched your own PCB, chemical etching, like the kind that you do with ferric chloride, and you can buy ferric chloride at, well, you used to be able to buy ferric chloride at Radio Shack. You can probably buy it at Amazon. You used to be able to buy it at Radio Shack. I don't know where you buy it now. But ferric chloride, it was a material that we used all the time, which does a really good job of etching copper off of a circuit board. Clever trick, if you've got a laser printer, you can print the PCB features, the inverse of the PCB features, on a laser printer. Set the laser printed page down on top of the circuit board, hit it with a hot iron. The material from the toner from the printer will actually mask out the board if you drop that into a chemical etchant. It'll etch away everything except for that stuff which is underneath the toner. So what you end up with is a pretty good and functional circuit board. But chemical etch is tricky because the etching process is a timed process. And if you can't control that very well, then you won't be able to do really small tracks. So this all goes somewhere. 10 mil tracks will be hard with chemical etch. 15 mil tracks will be better. 20 mil tracks will be probably realistic. Okay? If you're going to do CNC type stuff, like on my machine, like on the other mill, I can do 1/100th of an inch pretty well. There are other milling machines which have much higher resolution. LPKF makes one which has a much higher resolution, but this is 2200 and that's 22,000. So it's a very different price point. Okay? So this can do 10 mil tracks, 10 mil spacing totally reliably. I will tell you that a 1/100th of an inch end mill, and that's what we call the bits that we put into CNC machines, they will break pretty frequently, okay? Like one per board. So you have to be somewhat cautious of that because the end mills can be $15 a piece. So I tend to use 1/64th on this, and that tends to be okay, 1/64th of an inch. So there's a lot more material in here. I don't want to overwhelm you with all of the stuff in here, and I'm not going to read everything off of the slides. But the sweet spot really, 10 mil tracks by 10 mil spacing for most digital stuff. Okay. Via hole sizes. Here's the thing. Manufacturers don't have an infinite number of bits. Okay. So when they mill out the holes on your board, they don't have an infinite number of bits that they're actually going to use. Sunstone has a table of these are all of the tool sizes that they have, right? Your tool size is this. Your finished hole will be this, okay? Your tolerance will be this, blah, blah, blah. Every manufacturer will have a table that says that, okay? What you want to do is just work within their spec. If you want something 24-hour turn, quick turn prototypes, that sort of thing, or if you want something cheap, go with a larger hole, okay? They really hate making lots of repeat drill hits because it's one of the things that slows down production more than probably anything else, is that they actually have to keep it on a drilling machine while the drilling machine drops in, routes out the hole, and then comes up, and then does one of these, routes out the hole, and comes up. So a lot of those little prototyping boards that have that little prototyping area with big arrays of vias on them. Those things are really annoying for a manufacturer to do, and they'll charge you a lot for it. So they'll actually ask you, how many finished holes do you have? Beyond a certain threshold, they'll charge you more, okay? You usually won't bump into that threshold unless you're going to add that prototyping area on a board. But that insurance policy can actually be kind of costly. So you have to weigh up the relative merits of that versus, well, if it doesn't work, I'll just build another board. Or, well, I can add a connector and then I can do that other bit on a breadboard, right? So parts placement, generally speaking, we just don't put parts on top of each other. If you're going to hand solder things, parts placement starts to get to be a little bit more problematic. You want to try to get the parts placement with enough spacing between components that you can actually get in there and solder things, right? And you start low and work up, right? Because it's too hard to get the soldering iron tip in there when you've got a bunch of tall components sitting around it. So on this board, I did exactly the opposite of that. Because I put on the regulator and then I put in the two capacitors, and I'll actually pass this board around. So this is a board that we'll actually build after we eat some food. But you can see the regulator, and there's two capacitors which are right next to it, the two little blue components which are next to the black thing with the metal plate sticking off of the back of it. Actually, if you want to pass it up here, well, no, because you can't see it well on the camera. So yeah, you can ship it around. But I put those capacitors in after the fact, and it was just annoying. Just took way too long. But as far as part placement is concerned, generally speaking, we can get to within about 10 mils of other components, and it's no problem. From automated assembly, it's no problem. Yeah?
So the parts that are capacitive tend to platform off the board, and the other one's closer to the board?
So, well, so generally speaking, the way that parts placement tends to work is I tend to keep analog components isolated from digital components. That's one component. That's one aspect of it. I tend to keep the power supply as close to coming in to the board, right? So I don't want a connector for power and then my power circuit over here, right? If that's my power connector and my power circuit is over here, bad idea. So what you'll see usually on boards is that I've got a power connector. This is actually one of those DC jacks that you use for a, and then here are my regulator circuit right here. Okay, here's another regulator circuit right here. Both of these are creating the voltages that are required by this board. FPGAs have a lot of crazy, this is an FPGA, it's a field programmable gate array. Doesn't matter, it's got a bunch of crazy voltages that it requires. Okay, so to generate all of those voltages, I need a couple of different regulator circuits. So there's actually three. There's one here, and one here. And doing those three independent regulator circuits was cheaper than buying a chip which had three regulator outputs. But tendency would be, I want to keep that stuff isolated in one spot, I'd keep my digital stuff isolated in one spot, and then analog stuff isolated in some other spot. Okay. Opposite side of the board, again, is not isolation. Okay? You can't put all your digital stuff on the opposite side of the board as your analog stuff and then say, oh, look, they're isolated. Kind of doesn't work that way. Okay? So creating components, basically every CAD tool, we need to create components. We create a schematic symbol and a PCB footprint. The schematic symbol is what we use in the schematic. It's a sort of logical description of what's happening. It's the flow diagram that says these things connect to one another. And then we've got a PCB footprint or a PCB package. And we link those two things together, creating the relationship between pins on schematic and pads on PCB. Okay? The reason I bring this up is not because I want to start the process of doing that, certainly not right now because it smells too much like food. Is to say instead that when you're going to build components, the thing that we're actually fishing for as far as building components are concerned, you're going to have to do this at some stage, is to try to build components in a way in which on schematic they look good, and then choose components in a way in which when you get them to PCB, it's going to kind of fit within the constraints of the design. Manufacturers will make multiple different package types and that sort of thing. Some things will be incredibly small, little chip scale packages that you'll say, shit, I can't really even get a track through there. the milling machine can't get smaller than 10 mil tracks, 10 mil spacing, which means that on this board, the black one that went around here, I can't actually neck a track through any of these pads on here. So I can't actually make most of the physical connections on that board. So the selection of components is geared towards what are my minimum track requirements, what are my minimum track spacing, what's the pad-to-pad spacing on those components. Those things will drive how I actually select components, and then I'll build components that actually fit that selection. And then I group pins on schematic symbols and PCB footprints just to make things easy so my schematics look beautiful. And you'll see I am incredibly, I am like the master of building crazy looking schematics that I personally think are the best looking schematics on the planet. But you know, when I started to build, like a lot of this you can't do in Eagle because Eagle doesn't have the concept of hierarchy. But that free version of Altium, which is going to come out, that thing called Circuit Maker that I mentioned, that actually has support for hierarchy. Okay? And by hierarchy, what that means is I can separate my schematics into logical sheets, and then I can actually reuse those different sheets from design to design. So if I do a regulator circuit, some power supply thing, I can take that and isolate that and say, hey, I've got this power supply. I never want to do a power supply again, so I'm just going to reuse that sheet in every design that I use, or every design that I do. What's not happened, but we're trying to really encourage it, is that people are not sharing those things across people. They reuse those things, but they don't reuse them across people or companies in the way that people do in the software world. It's starting to kind of emerge, but the thing that I would encourage you to do is in Hackaday IO on the project site for Hackaday, I started a project called the Open Compatible Circuits Project. Okay? And the idea is that I wanted to just start throwing in schematic sheets which isolated specific functions and said, if you build this, it's going to work. Just don't think about it. It's a 5 volt to 3.3 volt regulator. Don't look at it. It's got this efficiency. It's got that much current output. It doesn't matter. I can black box it because, look, you know, how many people are going to leave here and go and build something which has a USB connector on it or has a regulator in it or has one of those things? And why would we all actually go out there and do that? You know, it just seems like such a profound waste of time. So I would definitely sign up for that project, but you'll see here in the way that I actually draw components and I draw schematics, you know, I create a schematic symbol, and my schematic symbol is isolated in a way in which, like, this thing is actually a multiplexer for SPI, and I've got two very clear SPI buses here that are controlled by some sort of control signal, and then I've got an output over here, right? And like just that configuration like that, setting that up in that sort of configuration like that makes it not only readable on schematic, but it also makes it super reusable. So when you looked at it, you could say, oh, SPI, SPI, SPI. Oh, okay, it must be multiplexing these two with that thing over there. So and this is the last thing that I'll kind of leave you with. We'll talk just briefly about building footprints. This is probably the one place where people get snagged up the most in creating circuit boards, is that at some point I have to put really small components down onto these pads, and they have to align perfectly with the pads. Okay? So a couple of things I would encourage you to do. First of all, there's a specification that IPC has called 7351. You can buy the specification, but it costs a lot of money and it reads like a phone book. However, there's a really cool tool . Oh. There we go. It's a really cool tool that you can download for free. Please don't do it here. Called PCB Footprint Expert, done by a guy from here, LA community. A guy named Tom Hauscher, used to work for Mentor Graphics. Here's the deal. creating a PCB footprint which is manufacturable at a professional assembler requires that the proportion of pad size to pin size needs to be very specific. Too big and the pins tend to float around because there's too much solder. It's like sticking a dinghy in a swimming pool sort of thing. They start to kind of float around a little bit, right? Or, you know, one of those things in a swimming pool. It's not a dinghy. A dinghy's like a little boat, right? They tend to float around. If the pad size is too small, not enough solder is there, the pins tend to come off. They might not come off right away, which is even more problematic because it's probably right after you ship it to 10,000 customers that then all of your component pins start to come off, right? What IPC tried to do was say, okay, let's look at all of the current surface mount technology that's out there. Let's look at all of the component pad geometries that we might need, and let's figure out, based on assembly equipment, what the actual pad size needs to be to connect specific pins. So what Tom did was take that standard, convert it to a series of calculators, encapsulate it in a piece of code, and then create a tool. You can download the free version, there is a free version, or you can pay him money for it. I paid him money for it because I use it so frequently that I actually started to feel bad. A moral compass thing, it was just, yeah, anyway. Basically, you come in here and you say, hey, I have one of these components, I have one of those components, I've got all sorts of different package types, pick the package type that I happen to have, click OK, and then what I do is go back to the data sheet from the manufacturer, looking at this information here, plug in the numbers, and you can either export to Eagle, a file that you execute in Eagle and it'll create the footprint. You can export to Altium. You can export to any of these other big CAD tools. A PCB footprint which will actually work for manufacture. That totally demystifies all of that stuff. If I said, hey, let's sit down and we'll do a workshop on how to design PCB footprints, we would be here all day just talking about PCB footprints. So the way to shortcut that is to say, go to PCBlibraries.com, look for Footprint Expert Lite, that's the free version, or Footprint Expert Pro. I didn't really find a difference between the two because the difference doesn't really apply to me. And you can actually use his calculator to do all of that stuff, and then you don't have to think about it. And you'll know that it'll be manufacturable. Okay? That takes all of the headaches away from that. There's no longer any question about any of that stuff anymore. So I would strongly encourage you to do that. I could sit here, as I said, and make this a really long discussion on how to design PCB footprints. But the few rules of thumb that I would leave you with are things like silkscreen boundaries, which IPC handles for you automatically. You want silkscreen boundaries and pin 1 markers on components, because you need to orient a component. Hey, what direction does this go? What direction does that go? Blah, blah, blah. You'll look at a chip and it'll have a little dot on there, but if I don't know where that dot is, then I got to go back into the PCB tool and look at it. So I tend to put pin 1 markers on things. I tend to put a nice clean silkscreen boundary around things. This one happens to be in green, but it's there. Silkscreen line width. I tend to keep the line width of silkscreen to about 10 mils. If you start to get too small, it can kind of vaporize. They can go as low as 5 mils pretty reliably, but if you get much smaller than that, your silkscreen will sort of disappear on you. And you'll start to get little spotches of silkscreen that actually fell off of the board. But this is ultimately what you're trying to achieve. Component pin which makes contact with a pad which has this very clean solder fillet. Okay? And that solder fillet happens in both the X and the Y. Okay? That IPC specification actually defines that for all of those different component types. Hey, this is the way that you do it, and it will be 100% manufacturable. Okay? They have 3 tiers. They have a low density, a medium density, and a high density that relate to how many components you have on the board. If it's really high density, then the pads have to get smaller. Your yield will be lower, but you'll be able to get more components on the board. How much lower depends on how many components you have and how close they are to one another. The thing that I would be more concerned about is keeping your components far enough apart from one another that they're actually reasonably reasonably isolated. 10 mils apart is fine, okay? Any automated assembly can do components that are 10 mils apart. And by 10 mils, I'm talking 10 thousandths of an inch, though apparently everybody in the room is a math major, so. Pad shapes, there's some rules as far as pad shapes are concerned. I'm not going to belabor the point. That IPC specification defines those rules. Tendency is that solder actually bonds better with rounded pads than it does with these rectangular pads. It just doesn't fill the whole area in the way that it does with the rounded pads. Right? With the rounded pads, it tends to fill much more evenly. With the rectangular pads, you can kind of miss the corners a little bit, and then there's less of a concentration in the corners. So we tend to do these kind of rounded rectangles or oblong pads like that for components of this type. Some manufacturers will give you specific, this comes from TI, will give you specific geometries for their components. So TI has a limited series of packages that they reuse because they've got one packaging line and then they've got their semiconductor line, which is actually building the semiconductor that goes inside of the chip itself. So their packaging line has tried to limit that to as standard a set of components as possible, and they will give you specific geometries that you can use for components. Err with the manufacturers because they've gone through that process. Periodically, you'll see this with the square pad up there and the round pads down below. As I said, I'll share with you guys a slide deck. In there are a series of tips. You can kind of run through the different tips. There's some links and whatnot, all sorts of different things that if you haven't actually looked at, I would definitely encourage you to look at. Soldering irons, you know, it tends to be a common question. What soldering iron should I use? What multimeter should I use? Blah, 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 blah. What tools do I need? Why don't we break for lunch? We'll come back and then we'll actually crack out Eagle. We'll actually start to create a schematic, we'll create a board file. I'll actually then take you through my schematic, my board file, and then we'll go ahead and plug that thing in, flash it, get JavaScript going, yada, yada, yada.
Okay. Hey.
Oh, hey.
Okay, so veggie pizzas are by the Hackaday.io banner. I suggest you do your due diligence if you're really thinking about being veggie pizzas. Because we think all the veggie pizzas.
Thank you for all the talk.
Oh, yeah, no, thank you, thank you.
Right here.
Oh, thanks, yeah.
Something I didn't hear about is the outline for the PCBs. When you make the PCBs,
Yeah.
you create the outline.
Yeah.
We didn't touch on that.
Yes.
And
Yeah.
I'm kind of interested because I want to understand how you do when you want to send board out for finalization. How do you actually create that and make sure it's actually the manufacturer doesn't hit you back with a big hammer?
Yeah, yeah. No, and we'll actually go through kind of a lot of those steps.
Okay.
And then if there's any looming questions after that, then definitely come back and ask me.
Perfect.
Where do I like learn how to, because I'm taking this like a soldering blah 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 class in June, starting in June, and I do work at a place that does billboards and all. But where, because I want to move to San Francisco eventually, where is there like a network of people who do? So
I run a couple of groups up in San Francisco. There's something called, if you just check out my profile on Meetup or whatnot, I run a group called Hardware Developers Didactic Galactic, which is like this group of a bunch of hardware folks that all get together and talk about hardware stuff. Starting in July, I'm actually going to do a third part of this workshop series that focuses on much more hands-on, actually soldering really fairly complex components.
The danger is that I'm taking a robotics thing right now, and the electrical people want to stick to the breadboard stuff, but they're not really interested in the thing, and then you get the software people who just want to program, and I'm like, no, hardware is important. Like you guys
I think the reality is that if you want to build anything that's going to work outside of your environment, you've got to put it onto a board. So I actually, starting in July, I'll actually take people through milling PCBs, and then also actually hand soldering stuff and like fabricating in a much more direct way. But look for it up in San Francisco. Yeah, no problem. No problem.
Tomorrow is you go through step by step a workshop.
Mhm.
Thanks a lot for
Oh yeah, no, I'm happy to do it.
He's actually gonna eat out his pizza. He's
Nah,
not gonna
it's not a big deal. It's not a big deal. I'm not feeling terribly well today anyway.
Yeah, especially that, because I know that's hard when you come there.
Oh man, I had such a bad night last night. It was crazy.
Sorry.
But no, it's all right.
Two questions. One, what are the best standards of file formats for schematics and boards and packages? Is there one or two that are really pretty, like if you can find it online, you can import that and do a lot of things?
Well, so it depends on the tool that you're using. It's all tied into the software, so it's like, you know.
So it's not an open source
Yeah,
kind of
there's
thing.
nothing open source for it, unfortunately.
Okay, so if you want to use Altium.
Well, Altium has a bunch of imports, so all the top-end tools have importers for everything, right? So, and even if they're not in the software, they'll give you one if they think that you're going to go use that other tool instead of theirs. So you just have to ask them and say, hey, do you have an importer for this? Altium's got all the importers built in, and we worked really quite long at trying to build all of the importers and exporters and stuff.
Okay.
But many of them don't. Eagle's got a few importers. Most of them are done with scripts. The KiCad has a few importers, not many. And then there's some other importers and exporters from different from some of the other manufacturers. Mentor Graphics and Cadence will all have, but they're all of that software starts at $5,000 and goes up per license.
Right. Absolutely. I'm really happy to hear Altium.
Yeah, Altium's has some good importers, and the Eagle importer is actually in their free version too. So then you'll be able to use all like the Adafruit stuff and Seed Studio and SparkFun and all of those things too.
What does this Footprint Expert make?
Footprint Expert will make any of those. So it'll do Eagle, it'll do Altium, it'll do.
You tell them what package they're going.
Yeah, yeah.
I mean, everything. It was kind of soon, but the layouts, everything.
What kind of pizza do you want?
I don't think I'm gonna eat.
Okay.
I actually feel really bad today. I tried to eat I ate a bagel earlier, and yeah.
Okay, 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 okay. Awesome. Hello. We're going to get started in about five minutes with community announcements. So if you have something you want to say, start thinking about it.
You actually just connect a wire hanging off it, or you can put a UFL on a carrier board.
Why do you have two URLs?
Because I was lazy and I wanted to flash this. I wanted to be able to flash two at the same time. I had a bunch of them that I wanted to flash, so this connector actually I was plugging into its keyboard, and then I was running two separate cables, and I was flashing two at the same time. And I just, I was like, oh, I want to flash two at the same time.
So did you write the tutorial for Hackaday?
I did.
I saw this, I thought, the problem I had a healthy tutorial, and I couldn't get it to flash anyway, so I had to finish two circuits, one to flash, one to turn off the power.
Yeah, so
maybe that was it.
No, what I did, like with this one, I set a jumper to change the voltage whether you're using the regular or not. Because some of these were 3.3 and some of these 5 volts. And then another jumper in there to switch between which transmit or which transmit I added split buttons in there basically when you hold, so you hold reset, hold down GPIO 1, let go reset, and flash. Then you can flash it. Because as long as GPIO, as long as GPIO 0 is low.
Yeah, but I had a problem with it. Still trying to use trigger GPIO 2.
Oh, yeah. I've never gotten it to work.
Okay, good.
I've never gotten it to work.
That's the question I had.
Yeah. Totally. Yeah, I had all sorts of weirdness like that. Kind of blew me away. Yeah, so I'll hand them out and I'll get some people to I would, yeah. I've got a bunch of USB to serial cables too and stuff like that. I would say come bring so bring 5 volts. Basically all I do is just 23 volts. Because I'm only using it to flash. It's not like I'm using it through the voltage provider.
Would you use 3.3 to stop the UR?
Yeah, because it's only the transmit in the PC, transmit from the PC that needs to be at 3.3. So I just go through, and that's actually what's in the schematic that will actually go through here.
I got frustrated with the clicking it to work, so I tried to go online to buy that.
Yeah, no, I was just like, I kind of got frustrated because I had all these wires hooked up on the breadboard. I was like, I have a mill. I will mill a board. But so like,
you intentionally place it right here so you can decide to on it?
Yeah. So then I put this voltage divider in here, basically that, so I got the transmit coming in from the USB to serial. I've got the voltage divider there, and then I break out from there, but then that is actually selectable based on the jumper. So if I'm using the 5 volt version, I have to jump that explicitly, so that way I can't accidentally drive it without that thing being jumped properly. So I've got like 2 fail safes there. So I've got that going on, and then I've got the regulator here where I have so this is also where I take B in and I have to explicitly jump it one way or the other. So I've kind of got 2 jumpers on this to make sure that otherwise, I mean, I could have done it. For some of the people that are attending, and I didn't want to make this a circuit problem. I wanted to make it a how do we actually solve this problem? Yeah.
You good with getting started? We're going to do a few announcements. You okay?
Yeah.
You don't look like you're okay. Every time I ask you if you're, are we are totally okay? I don't. I don't want you throwing up on me on
I won't throw. I promise you one thing. I won't throw up on you.
Oh, thank you very much. I'm super glad to hear it. All right, I'm going to get this started. Hello, hello. We're going to get started. So some people have come up to the front table and have been asking, can you guys hear me? You can, right? I sound very loud. Have been asking about 3D printing and all kinds of different questions. So we thought we'd spend about 15 minutes with community announcements, if anyone has anything to say. Anyone? Yeah, I saw you. Come up after.
Hello, my name is Mati. Big Data Day is coming up on June the 27th. Do check it out, bigdatadayla.org. It's going to be a free event thanks to our sponsors. We'll have 4 tracks, one on Hadoop, one on NoSQL, one on data science, and we should have a workshop. Check it out, bigdatadayla.org. Thank you.
Very little tiny microphone.
I'm having some trouble with 3D printing. If there's any gurus out there that would give some advice on some parts, I'd really appreciate it. I have some samples that are good and bad.
I think we all have 3D printing samples that are good and bad. It actually happens that we have a 3D printing company here. 3D printing people. Can someone come up here and announce yourselves? Yeah, you. I'll also take the opportunity to say, if you don't have a wristband for insurance reasons, we need you to register. Jasmine in the back is waving. Please go back there and register if you haven't already.
Am I supposed to say?
Just tell us about what you've got going on in that room and about your company and stuff.
Hey guys, I recognize a few faces around there, but I'm Diego from D's Maker. We're over here in Pasadena. We make 3D printers, and we have a special edition Buquito selling on the Hackaday store. So if you want a cool 3D printer with the Hackaday logo on it, you could check that out. We also brought a bunch of 3D printers, well, 2 of them, but I know what's a bunch exactly. We brought through 2 3D printers and a Microsoft Connect scanner thing to get 3D selfies later in the party probably. We're kind of setting that up. And yeah, and we also opened up a maker space next to our shop in Pasadena that we're about to start with memberships too. So is that cool that I plugged that?
Very good, very good.
All right, and yeah, if you guys have 3D printing questions or whatever, feel free to ask myself, or Metal is over there also. Yeah, his name's Metal. And he's over there helping with the scanning and 3D printing stuff. All right?
Cool.
Does that sound?
That's awesome. Yeah.
All right, thanks guys.
We have any other announcements?
Hi, my name's Jocelyn. Some of us are putting together a group of people to study machine learning to follow the Coursera course. If anybody wants to work on it, if you don't feel you're ready for it, we're going to do a little review of some topics. I would say before the data meetup, before the 27th, we'll focus on that, and then we'll try to launch it right after that event. And then also, if anybody's interested in doing more hardware-related stuff, we might get another group together and do that. So talk to me if you're interested. Meeting more often and working on these things.
I think you can give it to this gentleman. Okay.
Hello, my name is Mike. I'm one of the hats that I wear is a producer at Pasadena Media, and we're putting together a tech educational program. If anybody has any audio-video interest or prior experience, hit me up. It's absolutely free. You get free training, how to work cameras, yada, yada, yada. And we get an opportunity to go around. And also, Caltech also has a machine learning channel on YouTube for learning independently, not along, whatever. So, again, hit me up, Pasadena Media. It's right off of next to Pasadena Hilton, and it's got a brand new facility.
Anyone else? Am I seeing something in the back? This is Alicia White. She is a Hackaday prize judge, and we're pretty happy to have her here today.
So I just wanted to mention that I have a podcast about making embedded systems, building gadgets, and we just did 100, so if you want to know more about keywords in C, or being an entrepreneur, or hack, or Hackaday, yeah, embedded.fm. There are stickers on the table, or I have some more. And I'm speaking later. It'll be very fast.
Hi, my name is Wes Monroe. One of my hats is that I'm a member of the Pasadena Angels. So if anybody is in the fundraising stage, or is going to be at some point and has any questions about the process and so forth, they can talk to me. The organization, we're basically, if you aren't familiar with us, we're an angel investing organization with about 100 members. And you can look us up at PasadenaAngels.org.
Okay. Hi, my name's Sean. I'm a community advocate for Scale. Scale's Southern California Linux Expo. It's in February. He's representing the shirt today. It's the little gray penguin. His name's Troy. Not him, the penguin. But anyways, Scale's in February, so it's sort of irrelevant now. But Layer 1's coming up, like, at the end of the month, and nobody's mentioned anything about it, but I'm not part of Layer 1. I'm going to Layer 1, and you guys should too. Early pre-reg closes, like, on the 18th, and it's $100 if you register before the 18th. It's $160 at the door. I don't know if anybody wants to talk about Layer 1. Yeah, it's in Monrovia. Check out the website. It's put on by Null Space Labs. So, anyways.
Hackaday actually has a booth at Layer 1, so that's, I think, Matt, you're going to be there? Maybe? Yeah. Anybody else? Okay. We're going to break around 4:15 again for about, 20 minutes. Here you go.
Thank you. The extent of my coordination. All right. So where do we leave off? So we did a lot of talking about PCBs, and we're actually going to build one now. We'll go through that process. I will probably move reasonably fast because in the interest of time, I probably can't do a lot to keep everybody at the same level. So if you find yourself struggling to figure out where file open is, you know, we might not be able to bring you along for some of it. But if you follow along up here, I promise that I'll go through basically all of the same motions. And for those people that are interested in kind of going back through that loop, and for those people that are savvy with Eagle and that sort of thing and want to follow along, you're absolutely welcome to, and I would encourage it. However, we're live streaming the event also. It'll be on YouTube after the fact, so you can actually go back through the video. You can watch the video, just this section of it, and say, hey, I just want to figure out how he did this thing or that thing. How did he make the schematic do this or that, blah, 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 blah. But before we do that, I want to explain the problem, right? So sort of quantify what the problem was. So I mentioned earlier that the ESP8266 board is a 5-volt board, or sorry, a 3.3 volt board. Arduino, for example, is 5 volt. Your USB port is 5 volts, 500 milliamps. And the way that we talk to that board is through something called a USB to UART, or a USB to serial. What that does is it creates a serial port over the USB port in Windows, or, yeah, Mac. Sorry. I'm a CAD tool guy. We all use Windows. So to give you a sense of it, here I have a COM port, and you probably can't see it, but under the COM port it says USB to serial port. And the way that we do that is through a chip on one of these serial port converters from a variety of different companies. Cypress makes USB to serial converters. FTDI makes probably the most popular serial to USB converter. Okay? There are a number of other ones that are out there. Sort of 6 of one, half dozen of the other. It doesn't really matter. What you're doing is you're creating a UART over the USB port. What that means is I'm going to have a transmit line and a receive line. And the transmit and receive lines are going to connect into the transmit and receive pins on here. Transmit from the PC connects to receive on here. Receive from the PC connects to transmit on here. However, you can't really do that. And part of the reason why you can't really do that is because oftentimes the USB to serial converters are 5 volts. So you have to be sensitive to that. Now, the FTDI chip is clever in that it has a configuration mode that allows you to drive the IOs at 3.3 volts. And so oftentimes you'll find these little USB to serial converters that have a 3.3 volt configuration or a 5 volt configuration. Sometimes they'll have little jumpers on the back end that you can actually change that from a 5 volt mode to a 3.3 volt mode, that sort of thing. But this board that we created here, which I'm actually using as the flasher, the thing that I'm going to use to flash this little ESP8266 board here. That board is designed to take, doesn't really matter whether it's 5 volt or 3.3 volts, regulate that down so it's a regular 3.3 volts that I'm going to have, and then use that to configure the ESP8266. So by the time we're done, what we should have is a schematic that can support both 5 volts and 3.3 volts, that includes a regulator on it that does the level change there between the 5 volt level and the 3.3 volt. A voltage divider in there to handle the transmit from the PC to that thing so I don't overdrive it at 5 volts. A couple of other little nuances. Now, the way that I draw schematics, as I mentioned earlier, is the right way. No, I'm just kidding. I'm totally kidding with that. I'm totally kidding with that. No, the way that I draw schematics, I tend to be very visual, and I tend to lay out schematics in a way that make them very readable. Ergo, I don't often use Eagle to draw schematics. But that's a joke. It's a pun on Eagle. But I will do this in Eagle, but I want to first walk you through this in Altium Designer because visually it's just easier to kind of follow what's happening. So here's a top-level schematic. Eagle only has one level in the free version, so ignore this for a minute. Here's the top-level schematic. And the way that the top-level schematic is laid out, and I know that it's hard to read the text, so I'll just kind of explain it. I've got one schematic sheet. This is a subsheet, this little green box here. I've got one schematic sheet, which is a voltage regulator, okay? And basically what this has is an input here, which is 5 volts, which is coming from the USB cable. It goes through this regulator, which is an LDO, very common, very low-cost regulator, the LM1117. Now from TI, everybody makes a 1117. So TI makes one, ST makes one, kind of everybody who's into power makes one. So it takes a 5 volt input and it generates a 3.3 volt output. And it dissipates whatever extra power that I have in the form of heat. Now it can accept actually a much wider input range, okay? The output has a maximum current of like 1 amp, okay? So it's pretty substantial. But basically this circuit, which is this regulator up top, is where I'm going to take the power from the USB cable, and I'm actually going to use that to power the ESP8266. So I need to take the 5 volt input and I need to regulate it down to 3.3. It's pretty straightforward. We do this all the time, okay? Linear regulators, terribly inefficient. I mean, regulators by definition kind of fall into one of two categories, linear or switching. Linear regulators, we dissipate power in the form of heat. Switching regulators, we manage power by switching things on and switching things off. That makes them incredibly efficient. And the net power output is a function of how frequently we turn it off and turn it back on again, okay? Switching regulators are just way more complex than this circuit needs. So in this case, we're going to use a linear regulator. And likewise, you can't find a lot of through-hole switching regulators. So because tomorrow anybody who comes, I'll give you one of the boards, we can sit down and we'll try to go through the process of soldering them together. I wanted to give you something that was through-hole, that was just easier for you to solder. So this little green board, in that regulator circuit there, I've got the 5-volt input, which is coming in from USB. It goes through the regulator, and it comes out as 3.3 volts. Now, when it comes in off of the USB connector, and this is a USB connection here, I wanted to account for the circumstance in which, let me kind of zoom in on this a bit. I wanted to account for the circumstance in which I had one of these little USB to serial adapters, but it was already 3.3 volts. So the way that I account for that is I actually have a jumper here, a two-way jumper. And this is a really common convention that I use all the time for sort of cheap and easy ways to deal with stuff. I have a really simple jumper on here. If I jump it this way, I'm using 3.3 volts. If I jump it this way, I'm driving it at 5 volts. Okay? If I jump it in the 5-volt way, it pushes the 5 volts into the voltage regulator, and it steps it down to 3.3 volts. If I jump it on the 3.3, I don't need the regulator because I have a 3.3 volt input at that point, and then I just go ahead and drive the chip directly. Okay? So depending on where I put that jumper, that's actually going to determine whether it's 5 volts or it's 3.3 volts that I'm accepting as the input. Okay? From there, that's actually going to determine how things connect across the board. Now, this is the input from these little USB to serial adapters, and I'll pass a couple of these around. You should take a look at them. You can buy them from SparkFun and a couple of other places. There's tons of these out there. They're kind of all over the market. If you look at them, you'll see that they have silkscreen, which indicates just what the I/O pins are and that sort of thing. On the back side, they'll have a little collection of a couple of pads. There'll be 3 pads. And they'll have one of the pads is connected directly if it has 3.3 volt output. If I slice the connection between the 3.3 volt and the other pad, and then I solder the other one together, I can actually convert it to a 5 volt. They have a 5 volt one, which I can configure to be 3.3. So they're actually configurable. If you flip them over to the bottom side, there are 3 pads right next to each other. And I can slice in between there, breaking the connection between one set of pads, solder a connection between the other set of pads, and actually change the I/O voltage on those things. But in the event that I had a different USB to serial adapter, which I have quite a few actually up here, I may very well need to be able to regulate that to something, to some sort of different voltage there. So this is the regulator circuit, just taking a look at it closer up. And most linear regulator circuits look like this, right? So you've got a 5 volt input. You've got a couple of capacitors on here, decoupling capacitors, whatnot. And then you've got the regulator itself. Virtually all linear regulator circuits look like this. There's one variation on that, very famous variation, which comes from Bob Weidler and Bob Dobkins, who were famous for creating a linear regulator that had an adjustable output. And the way that they did that is with the addition of a couple of resistors in here, simple voltage divider network, I could configure the output to be something which was some function of the input and that voltage divider in there. So they managed to isolate that and separate those two things so I could have a simple voltage divider on the outside of it. It was a very, very famous chip that kind of put those guys on the map. And Weidler's a nut. He was a very interesting guy. Unfortunately, he died quite a while ago. And there's some pretty interesting stuff on Bob Dobkin that if you look up online, he's actually in a semiconductor museum doing a video kind of discussing the sort of early origins of some of the things that those guys were working on. And it's just great theater from an engineering standpoint. It's great to watch. Anyway, so, very simple sort of regulator circuit. And at the top level, now this part might look a little more complex than it needs to, but let me kind of explain what's going on here. When this is operating at 5 volts, I've got a transmit pin which is coming in from the PC at 5 volts. If it's operating at 5 volts, I need to step that down to 3.3 volts. So there are a couple of different ways to do that. One way is to use a level translator, which would be kind of the ideal way to do that. But there's a lot of thinking that kind of has to go into it. It's a pretty expensive chip to add. And in this case, I really don't need it for the limited time that I'm actually going to drive this thing. So instead, what I'm using is just a very simple voltage divider, okay? And this voltage divider with 1K up top and 1.8K down below gets me to about 3.26 or 3.28 volts or something like that, which is plenty good for that to work with this ESP8266. It's not a perfect 3.3 volts, but the ESP8266 has a nice range in there that I can, I'm certainly within the window of the range on that. So that voltage divider is only used when I want to connect this to the PC and the level that I'm driving it at is 5 volts, okay? Going the other direction, it doesn't matter, because going the other direction, that chip, specifically that FTDI chip, can accept either a 3.3 volt input or a 5 volt input, and it will register both of them as being a logic 1, okay? So it doesn't matter going the other direction. It's only when I'm driving the ESP that I don't want to drive it at 5 volts. So that voltage divider in there is to prevent me from driving it at 5 volts. Now, over here, this is the connector for the ESP, all right? I've got a push button here on reset. I push this down, it takes reset and ties it to ground. Reset is active low on that device, so if I press that down, it'll actually reset it. I've also got another push button here on a pin called GPIO 0. And if you look at the data sheet for the ESP, if you want to flash the device, it needs to be with GPIO 0 tied low at the time in which you start flashing the device, okay? So the easiest way to do that with these push buttons is to hold down reset, hold down GPIO 0, lift up my reset. Now GPIO 0 is low, right? I click my button to go ahead and flash it, and then I can let go of the pin, because it just needs to be low when I start flashing it, okay? Once I do that, then I can let go of the pin and I can leave it alone. So that's why I did the push buttons the way that I did. It was just there so it would make it easy for me to switch it into programming mode and then normal use mode. So GPIO 0 needs to be tied low for programming mode, okay? Only when I'm flashing the device. Not when I'm writing my own program to it, but only when I'm flashing the device, okay? So I put a couple of push buttons in there. I've got some pull-up resistors in here. And pull-up resistors, for those people that don't know, pull-up resistors, we just use them because we want to put things into a known state, okay? I just don't want things to be in some unpredictable state. So I put a pull-up resistor in there, and I know that that's explicitly pulled high under the circumstance in which that's not then explicitly pulled low. So I've got a very distinct state for that thing, okay? Over here, I've got another pull-up resistor. In pull-up resistors, the strength of the pull-up is inverse to the value of the resistor. So a 10K pull-up is a weaker pull-up than a 4.7K pull-up, okay? You'll see people use 4.7K all the time. You'll see 10K used all the time. Those tend to be the sweet spot, okay? Some things will have very explicit specifications for what pull-ups you should use, JTAG and things like that. But in general, pull-ups are either 10K or 4.7K, okay? In this case, I've got my I/O pins over here, I've got my transmit pin, and then I've got another one of these two-way jumpers. And this other two-way jumper says, hey, do I want to connect to that, which goes into the voltage divider there, or do I just want to go back to that USB connector, okay? Because if that USB connector is at 3.3 volts, then I can bypass that voltage divider altogether and just connect to this up here, okay? So then I'm only connecting to this transmit up here. If I need to go through the voltage divider, then when I jump this over here, it'll actually connect from there to here, okay? So it gives me some options. So I put a couple of jumpers in there because the jumpers were just easy and they're very explicit. There are other ways that I could fine-tune this, make this more sophisticated at the circuit level so you didn't have to think about it, but I think this is a nice sort of visual way to understand things. And then I've got one LED on here which is actually tied to GPIO 0, okay? And that's the LED that we're going to turn on and off when we actually flash this thing with Node and set up a web server and or with Node MCU, set up a web server, and then actually toggle the pin. Okay? So this is the circuit that we're actually going to create. And just to kind of take you through this in the Eagle context, let me go ahead and close this project. So for those of you that have Eagle, if you wanted to open it, you're welcome to. So Eagle uses projects, Altium uses projects, lots of different design tools use projects. The model for how they use them is slightly different, but it's not hugely different. So if you learn one, a lot of the same sort of methodology will apply to other ones. Okay? In Eagle, you create a project, you add to the project a schematic and a PCB file, right? Or a schematic and a board file. The board file is your circuit board, that's your physical implementation. Your schematic is your drawing, that's your logical implementation. That's going to show you how things connect. Your PCB is going to be how they actually operate in the real world. So, you know, here's my schematic in this context, and here's my PCB, right? This PCB looks decidedly familiar if you look at the green one up here, and then compare it to that, all the way down through to this piece of silk screen, which I threw on there just because I happen to have it. Despite the fact that I'm actually using the old Hackaday text, but yeah, that's okay. Sorry, I'm bad with branding. All right, so I'm going to go ahead and create a new project. And I'll just call this ESP8266. And this is Eagle's control panel. So this is kind of the origin point for a new design, but you won't spend a lot of time in this space. Once you've got the control panel, once you've gotten past the control panel into creating a new schematic and into creating a new PCB, you won't spend any time back in the control panel. Now, there are a whole host of libraries that are available for Eagle that are not pre-installed, that if you don't have them, I would encourage you to get. And you can get them from Farnell's website. So if I say Farnell Eagle libraries, so there's a whole collection of libraries here that you can download from different manufacturers, and there's actually some good stuff in there, okay? I will caution you this, okay? Not every library is created 100% accurately. If you imagine that you create something with 1,000 components in it, getting every pin name and every pin number right, there's a likelihood that something is going to be wrong. So you never take for granted that the library was 100% right out of the gate. You always look at the pin numbers and reference them back to the data sheet to make sure that it's right, okay? Likewise with footprint geometries. If ever I borrow a library from somebody, I would go back to whatever my library is, or whatever my data sheet is, and I would actually check that library, that footprint, to make sure that the footprint matches what's in the data sheet, okay? And that just ensures the fact that I don't have to print this thing, or produce this thing twice. I will say that one trick that does work is, and it's kind of a crude way to approach it, is to just print one-to-one. And then take all of your components and set them down on top of there, and if anything looks weird, change it. And that's a super easy way just to get kind of a visual test of, oh, okay, yeah, actually, yes, this makes sense. Because I've done things where you get all the way down 13 or 16 or 18 characters into a part number, and it's that one last variation. Oh, this is the dash S, and the dash T is only, you know, it's slightly different than that. And oh, okay, yeah, that's a problem. So these, if you want to download them, when you come on here and you download, and I probably shouldn't say this, they do prompt you to usually log in. But if you know anything about the web, you can actually go into here and block out this mask that's over the top of it and just not register and just download the stuff. But I wouldn't encourage you to do that, because that would be unfair to the people who put their tireless hours into building those library components for your consumption. But if you were so inclined, you can go into the page source and just block out the mask over the top of it and actually get at the library information. I mean, I'm just saying. But you didn't hear it from me. You heard it off of a video on YouTube. Okay, so ESP8266. This is my project. I right-click on the project. I select New Schematic. That'll create a new schematic document, okay? Now, the schematic document, again, all we're going to do in here is lay down some components, wire them together, and then generate the source that we're going to use to build the printed circuit board. When you place the components, this origin point, or this cross down here is the origin point. That's 0, 0. So everything should be up and to the right of that, okay? We do everything up and to the right of that. Different versions of Eagle, if you buy the paid version, will have support for multiple sheets. But in the interest of this group not necessarily having a paid version, that sort of thing, we'll do everything that I did in the other context, but we'll do it all on one sheet, okay? That doesn't mean that we can't sort of group things into logical kind of meaningful groups. You can also still go through and copy and paste from one version of an Eagle schematic into another. So if you go to, for example, Adafruit, their GitHub repository is a wealth of a bunch of different Eagle schematics. If you want to copy and paste, there's one caveat to that. You actually have to have two processes running. So like in Mac, you actually have to go into the package and open up, show package contents or whatnot, and open up and launch another Eagle instance. In Windows, you don't have to do that. You just launch the executable again. But on Mac, you go into the application and then you launch a second instance of it. Once you have two instances, you can copy and paste between the two, okay? But you have to have two independent processes running to be able to copy and paste between the two. So in this case, this is a blank Eagle schematic. Now, Eagle, by default, you have this command line along the top. That's always active, okay? So up here, if I said, if I type the word grid, for example, it'll actually show up in this command line up top. If I hit enter, that'll actually bring up a dialog box. If you learn Eagle's built-in commands, you can do some things reasonably fast. If you can type faster than you can click or find menus and things like that, you can make things run reasonably fast, okay? A note on schematic grids. We never change the schematic grid, okay? And the reason we don't change the schematic grid is that you're going to wire on that grid, and the pin-to-pin spacing is always 100 mils, or 1/10 of an inch, okay? So if you change the schematic grid to something that is different than that, when you draw the wire and you connect it in, or try to connect it into a component pin, you won't actually be able to make the connection. The worst case in that could be that you think you make the connection, but you don't. And now you're in a circumstance in which that doesn't translate to PCB, and now you don't have a circuit board in which you have a physical connection between this pad and this pad over here, right? So we've got to manage that, be somewhat careful. Now you do have an alternate grid, and the alternate grid is great when you want to position things like text, okay? So if you hold down the Alt key, you can move text around and that sort of thing, particularly component text and that sort of thing. So if I wanted to get component designators and stuff around, that sort of thing, it's very easy to do. All right, so I'll go ahead and click OK on this. I'm going to go ahead and place a component. Now, you've got a series of toolbars off to the side over here. All of those same toolbars are accessible through the menus. You can also do your own shortcut bindings. I won't get into detail, but you can set up your own shortcut bindings and bind them to commands that you would run through the command line. So you can actually set up some shortcuts and try to make things run a little bit more smoothly. Once you get into the psychology of the developer that was actually building Eagle, you start to kind of understand how things were done and why they were done certain ways, okay? It took me a little while, but once you kind of understand it, and I'll show you right now one example of that. Once you kind of understand it, it'll all sort of click for you. Now, I clicked on this icon over here. If you hover the mouse over it, it'll say Add. By clicking on that icon, it's going to go ahead and load up all of the libraries that you currently have loaded. And if it's the first time that you've launched Eagle on the computer, it takes a while. Particularly if you have a lot of libraries like me. So I downloaded all those libraries and installed them, and Eagle's going to go through and parse all of them and figure out what all components are in there, and voila. True story, and it's just anecdotal. I was watching a tutorial on their website at one point, and the developer who was explaining their new hierarchy system was like, and now we'll go ahead and place a component. And then he goes in and he clicks the Add button to place a component. And I promise you, it was 3 full minutes of just dead air. just dead air. Like, and I thought, wow, you know, you could like just cut that section out of the video. Like, you're not even on camera. Like, just like clip, you know. Look, and 5 seconds later, it loads 10 million libraries. Complete dead air for 3 full minutes. It was great. It doesn't take a lot to entertain me. So now, down here, I've got a search option. And in the search option, basically, you can use wildcards, like asterisk is the wildcard. The first thing that I want to actually do is handle the regulator circuit. So the regulator circuit involves a voltage regulator called the LM1117. And there's variations of it. ST makes a version of it. National Semiconductor, now Texas Instruments, makes a version of it. It's a very common device, okay? So I'm just going to type *1117* and hit enter and see what pops up. Now, you may have slightly different results than I do, okay? That's okay. Don't freak out. Because I have the National Semiconductor libraries loaded and a bunch of other stuff, there's probably a Burr Brown version of the part, though they haven't been in business in like, you know, I don't know, dog's years. I'm going to place, you'll notice here that the LM1117 has a hyphen, and then there's a series of numbers after that. There's a -3.3 and a -5.0 and yada, yada, yada. That's the output voltage value, okay? So if I choose the T, this one is the TO220. So this is that same package that's on here, the one with the little metal plate on the back side of it. Okay, that's the through-hole version of that. So I actually went into, I'm in NSCB. You might not have that library. If you don't, you'll find one under ST, which is pre-installed with Eagle. And just checking on my, I look on my Mac, because my Mac doesn't have any of the libraries set up. If you go into v-reg, I think, which is pre-installed, then under v-reg, you'll find a top-level category, which is LD117A question mark. Scroll down that to where you get to LD117A V333. It's like the second to the last one in the list. It should say TO220 L1 blah, 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 blah. Should be the second to the last one in that list. Okay. In this case, I'm going to use the TI version of it. It's what I happen to have. I actually don't like the orientation of the pins. That's okay. I'm going to show you a trick in Eagle that allows you to kind of tweak that. I'm going to go ahead and click OK, and I'm going to drop that component into the schematic. Now, just click to drop the component. If you right mouse, this is why I suggested bringing a mouse. If you right mouse, it'll actually rotate the part. Okay. Some things with Eagle, if you control and use the mouse wheel, you can zoom in. Okay, right mouse rotates parts, it's pretty common. In this case, I'm going to hit escape. And if you notice, as soon as you hit escape, it actually throws you back into this dialog. This is where I was talking about getting into the psychology of the person that wrote it. So what they were thinking about was, and this actually is a throwback to the old 90s way of doing things, is that I would hand draw a schematic first. And then from my hand-drawn version of the schematic, I would go into a CAD tool and I would lay it out. And what that meant was is I already kind of had a parts list in mind with very explicit parts. So when I hit escape, it would throw me back into the dialog and I would just place the next part. And then I would hit escape and throw me back into the dialog and I just place the next part. It's a very old sort of traditional approach to doing things where you started first with paper and then you went to a CAD tool. We kind of don't do that very much anymore, okay? Periodically I'll draw something out on a piece of paper if I'm just thinking through a problem, but it's not to the point in which I actually start writing part numbers underneath it, okay? So it's kind of an old way of doing things. Doesn't mean that it's necessarily wrong, but it's also not right. And deleted the library? Yeah, so, yeah. Any other questions? No. Did you accidentally hit drop? Okay, so, yeah, that's not good. What was the mindset of the developer at that point? So like that was like before they started drinking, and that was like, you know, happy hour on a Thursday. Dude, I got this idea. We're gonna implement this totally awesome new way of doing things. You can just delete library components at will. Yeah, I don't know what the psychology of anybody would be to do that. Now, I want to place a capacitor, because if you remember that regulator, the layout of the regulator was input, capacitor, output, right? Standard form for low dropout regulators. It's just what we do every time. So if you're using an LDO and you don't do that, you should ask yourself a question, why am I not doing that? So I'm going to look for a capacitor, and in this case, I'm going to look for something which, these are all surface mount. I don't want the ABX. So Eagle's got a couple of different capacitors. So if you go into, there's something called capacitor WIMA. And I'm just going to go ahead and place the C5 2.5. And I'll drop one on the input side and one on the output side. Now I'm going to hit escape, but then I'm going to hit escape again to close out of that dialog. Right? So now I've got one capacitor over here, one capacitor over here, and I've got my regulator. Now for those of you who are using the other regulator, you might have an input pin and an output pin and a ground pin. That looks much better, okay? And I really like that look. For those of you who want to learn a little more about Eagle, you can modify some of the existing libraries. So if you right-click on a component and you choose Open Symbol, you should be able to launch into a library. Now I got to set up my library pads first. You should be able to launch into a library and actually modify the symbol, which would allow you then to move that pin down here, okay? Rather than waste a lot of time with it, I'll grab the other one that I suggested you use, which is the one from the VReg lab. And that's got this one right here. We'll click OK. Now I've got something which kind of looks like that, okay? LD version versus the LM version is the difference between the ST version of the part and the TI version of the part. Functionally exactly the same. Behavior exactly the same, okay? So I'm going to go ahead and just move this part. And to move stuff in Eagle, you right-click and choose Move, and then you can move it around. Each component or each element will have a little plus sign on top of it. If you don't hit it in the plus sign and it's kind of around other stuff, it can become difficult to select things. So what you want to do is be sure that you find the origin point, and the plus sign is the origin point of that element, okay? You want to find the origin point, and then you want to move that around, okay? Or you want to pick it up from there. Now, once it's moving, and you can right-click, and the Move command will show up on the right-click menu. You also have the option to come over here and choose the Move command from the toolbar. But once it's actually moving around, then I can kind of move this stuff and figure out exactly where I want to lay it out, get things a little bit closer to each other. A lot of the commands are modal. So once you're actually moving things, you're moving things until you explicitly stop moving things. So even if I hit escape, move is still highlighted in the toolbar over there because I'm still in move mode, okay? It's kind of unfortunate in some cases because you'll find that you're actually in another mode and then you need to stop. If you do need to stop, there's a little stop sign up here. And you can actually stop just using that, and that'll actually take you out of any existing mode that you're currently in, okay? Now, a couple of things that I actually need to tweak here. First of all, I don't like the way that that reference designator text is sitting at the bottom of the component. I think not only does it look ugly, but I don't name components IC1. That's some weird thing that nobody uses except for, yeah. Anyway, people do use it, but it's not a convention that anybody I am friends with uses. And then I need to change the values of these respective capacitors, right? so I have some sense of what capacitors I need to order. So I'm going to go ahead and right-click on this, go into its properties, and then I can say my value for my capacitor, and this value comes straight off of the reference design on the data sheet for this particular component, for the LM1117. The value that I'm going to define for the capacitor is going to be 10 microfarad. Right? So 10 lowercase u capital F. So that capacitor and the other one are both going to be 10 microfarad, and both of those come straight out of the data sheet. Typically, I use ceramic capacitors with a much, much smaller value than that, but this comes straight out of their data sheet. So we'll follow their data sheet for now. Yeah.
Could you repeat again what part number that was on that?
Oh, sorry. So this regulator right here is, the capacitor? Sorry. Yeah. So if you go into, so it's C5/2.5, open paren C, closed paren, whatnot. So if you just do C5/2.5 star, you should find it. Yeah, no problem. So I'm going to go in and change the properties of this one also. Change this to 10 microfarad. Bonus points for anybody who remembers the part number of Weidler and Dobkin's famed first adjustable voltage regulator. It was the 317. It was indeed. And it was 1972, something like that, when that came out. I actually wrote a great blog post. If ever anybody wants to read my blog, which not many people seem to. So if you go to phi.supplyframe.com, oh, look, it's my mill. I also do like a bunch of stuff based on big data, because we do a lot of vertical search for electronic components. So things about like what are the most popular component searches, that sort of thing. Anyway, there is a discussion in there of Weidler and Dobkins and that sort of thing, and the LM317. Okay, so now I want to move the text around, because the text isn't where I want it, and I actually want to be able to adjust some of these various names and that sort of stuff. And to do that in Eagle, mind you, just so you understand where some of this comes from, Eagle comes from a company called CADsoft, which originated in Germany. Okay, so much of what they're describing to you is actually a translation into English, which seems to have first been translated into Japanese and then English, because some things don't make a lot of sense, and you'll see some stuff later that really exemplifies that. But so if you want to explode a component, because that's the terminology that the industry created 20 years ago, you instead smash the component. So you right-click on a part and you choose to smash it. Okay. From there, once something has actually been smashed, then all of the elements are independently selectable. Okay, so I can move the text from here to here, and I can kind of jive that up here if I wanted to. I can grab this reference designator, move it up here, that sort of thing. And I can sort of fine-tune the magic. Now here is the one instance in which you can hold down the Alt key on schematic and be kind of cool without using the grid. And that's because if you hold down Alt while you're moving something, then you'll move to that second grid that we saw earlier, and that lets you sort of fine-tune exactly where you place text. Okay? So if I smash, for example, my capacitor over here, if I just try to move the text on grid, it's very hard to get it in a spot that kind of looks okay. But if I hold Alt, then I get a much finer grid. And then I can say, okay, you know, I want this piece of text over here, and I want this piece of text up here, and build me something which looks a little more beautiful than what I had previously. And we'll move this over here. I'm going to fine-tune the magic. Move this over here. Now you will notice, and you'll care about this more in PCB, you will notice that up in this far upper left up here, you've got not only an indication of what grid you're on, but then also what your XY coordinates are. And that's useful for doing text alignment also in schematic, but it's probably not as meaningful. So up here in this area. So in this case, I'll go ahead and just kind of jive these things into place. I don't want to try to go too far with it because I think it'll take valuable time away from the stuff that we actually want to do. So, okay, cool. Got a regulator. I want 5 volts on one side. I want 3.3 volts on the other side. And I need a ground connection. Okay? Ground connection is going to be here, here, and here. 5 volts, 3.3 volts. And I need wires to connect those things together. The way that Eagle does power connections in general, if I go back to add over here, is they actually do them as components. So if I type 5B, let's see here, will it show up as 5B? Or do I have to do VCC or something like this? Yeah, probably have to do VCC. So, oh yeah, look, it's VCC. Hooray. Okay. So they've got a couple of different supply symbols. They've got that weird arrow, and then they've got the circle. They've got some other stuff in here. I think they probably have VDD. I don't know if they have 5V0. No. Do they have 5.0? "19-inch slot Euro cards." Wow. Yeah, that's a throwback, man. Woohoo. So I'm going to do these as VCC. So I'm going to drop one connection over here. I'm going to hit escape. I'll do trying to find where 3.3 volts actually is. There we go. So if you do +3 and then star, you'll get your 3.3 volt, which will be under the supply category, or under supply, the supply library, supply 1. So I'll click that, drop that in over here. That'll give me my 3.3 volts. God, that looks terrible. If I hit escape again, the last one that I need is ground. And ground is ground is ground. In this context, ground is ground is ground. Now, typically we use arrows for ground, okay, pointing towards the ground sort of thing. Typically we use either circles or bars for power connections. The use of the arrow for power connections is very uncommon these days, so the fact that they actually have those things bound to that is just an indication of the fact that the tool is reasonably old and the implementation of some of these components is just kind of outmoded. But nevertheless, we can still get there with what we have. So the ground symbol that I'm going to choose is actually from supply 2, and I'm going to get the one that has the arrow pointing down on it. And I basically need 3 of these. So I've got something which looks like this. I'm going to hit escape and hit escape again, and I've got a schematic which kind of looks like that. Okay. Now, for those of you with a mouse, if you hold down the center mouse wheel, you can move things around and pan and whatnot. For those of you on a Mac, if you just use multiple fingers, you should be able to pan around. For those of you on a Windows machine who don't have a multi-touch keypad, I'm sorry, because it just sucks. There are tools for recentering. So under the View menu, you can redraw that sort of thing. If you use F5, it'll center around wherever the mouse is. Okay, cool. So a little bit of wiring, a little bit of kind of text manipulation. You realize that with kind of layout and the amount of effort that's involved in kind of moving text around and stuff like that, why the Arduino schematic for the first revision of it looks so terrible. Sorry. It does. It doesn't read very well. Brilliant board, but the schematic doesn't read very well. Okay, so the next thing that I need to do is actually wire these things together, and there's a wiring tool over here. Looks like a pencil with a little line on it. And I'm going to grab the pencil, click, and just start wiring. Never assume that Eagle will make an explicit connection, or sorry, an implicit connection, because 9 times out of 10 it will not. So if I drew this line from here to here, simply by virtue of this pin being coincident with that wire, one might intuit that those two things should be connected. Eagle will not connect them, okay? And you'll find all sorts of circumstances where that little nuance plays out. And it actually becomes really problematic if you're not careful and don't check schematic very closely to make sure that all of the connections are there. Now if I pick up from that pin and I connect to that pin, it will still later yell at me about the fact that those two pins, or that there's no junction dot on that pin, despite the fact that it knew that there was no junction dot there, and thus one could infer that it could programmatically just add it for me. But sorry, hater's going to hate. So create a couple more connections here. And now, I've introduced a bunch of errors into the schematic already, and that's okay, because part of this is an exercise in how to figure out whether or not you have problems. So this isn't connected, because I just did exactly what I said I shouldn't do. This is connected, but there's no junction dot, so it'll probably throw an error at me from that. There are some other little things. We'll fix all of that stuff. But for now, let's go ahead and move on to the next part of the circuit. So this is so far what we've basically got. Okay? So far we've got something which is this. Oops. So we've got a 5-volt input, we've got a regulator, we've got a couple of capacitors, and an output. Cool. That part is done and dusted. Nothing left to do on that. The other part is this. I've got a header, which is basically a 6-pin connection. It's a right angle, hangs off of the board. And that's where this programming connector plugs into these pins here. So that plugs into this like this. And I'll pass the kind of the whole structure around so you guys can actually take a look at it. So you'll see, I've got a set of pins here. This plugs into this using this right angle connector off of the side of the board there. Once you look at the whole structure, then the purpose of some of the things on that other board makes sense. Yeah. So if you right-click on the wire and choose delete, then you can delete it. Now, if it's just a matter of kind of re-cornering a wire or something like that, there are some options in here. I think there's, actually it's PCB, sorry. Yeah, but you can right-click and delete stuff. Once you're in delete mode, though, just be careful because it's modal. So everything else that you click on, you're going to delete. All right. So the next thing that we have to sort out is that programming header. And again, the programming header is just a 6-pin right angle header. And what that is it sits into the board. It's got 6 pins coming off of the side of the board. It's right angle because it bends at 90 degrees. And it does one of these, kind of jogs off to the side of the board. It's got 6 pins. These are the names of the connections on there. So it's got an input voltage. I don't really know what that's going to be yet, but we'll make something up. It's got some other signal names on that. And then down here, I've got this 2-way jumper, which I'm using. One side here for VN, and then 5 volts on one and 3.3 volts on the other. So what I need is a 6-pin right angle header and a 3-pin jumper, and everything else should be okay. Okay? Typical jumpers on a board are 100 mil spacing. That's really common for jumpers. So, or for headers of all types. So these typical header pins here, and then the types of jumpers that you actually stick on a circuit board, those are all at 100 mil spacing. And basically you slide the jumpers on top of the pins. Now, when you look at these, and I'll share them around, when you look at them, you'll notice that they can actually be broken away. So, they're really designed don't ever buy the 2-pin ones. Buy like the 36-pin or the 40-pin ones, and then break them down into the smaller ones that you need, okay? If you're going to do automated assembly, you might want to buy the ones which are 2 pins only if you wanted to put jumpers on there or something like that. But if you're going to do anything which is hand soldered, just buy the 40-pin ones because it turns out to be considerably cheaper. So, this is your typical bag of jumpers. You'll notice that on the outside of these jumpers, they've got a little metal wire which cuts across it. And that's actually a place that you can hook an oscilloscope probe to. So you can actually hold a probe against whatever that jumper is going to be. But I'll pass them around. You guys can look at all the fine and wonderful props. I feel like the prop master. Okay, cool. So jumping back into Eagle, I know that I need that header, so I'm going to go back to the add command. And if I just go down here and I type header, there'll be a bunch of them in here. So there's a library called con lstb. The ones that are prefaced with MA are male. Though, to be honest, it doesn't much matter, okay? Now, the thing that you'll notice is they don't have a right angle version of it. So the first one that they have that's right angle, just seen here by the picture, is actually, with the series of pins hanging off the edge over there, is actually the 7-pin version of that. It's okay. We can use what looks to be a vertical one. So MA06-1. And then we can drop whatever we want into it. It can be a right angle connector. It could be vertical. Doesn't really matter. Okay? Because the pin-to-pin spacing isn't going to change. Whether I drop a right angle connector in there or I drop a vertical one in there, it doesn't really matter. Okay? So if I check MA06, click OK, and drop that in there. Anybody's guess where SV came from as a prefix for a header? These little designators here, these are the unique identifiers for all of those components. The SV is like nobody's convention. Like 0 people have ever used SV. Sorry. I'm going to be known as the complainer now. I need one more, which is going to be that 3-pin header. So I'm going to grab MA03-1, and basically what that leaves me with is something like that. Okay? So I've got MA03-1 and MA06-1. 06 is my 6-pin. That's where that FTDI connector is actually going to make contact with that. And then this is actually going to be my jumper. And I'm going to jump one side or the other, depending on whether I have a 5-volt input or a 3.3-volt input. Okay? So I'm going to hit escape twice and just get out of that mode. Come out here and actually do some wiring. So the way that the pinout on that connector is laid out, and I just sent all those boards around the room. The way the pinout on that connector is laid out is pin 4 is power, pin 6 is ground. Okay? Now, I need power to be different than the other power, because this is the power that's coming in, but I'm going to jump between 5 volts and 3.3 volts. So we may actually change the other one to 5 volts. Let me explain. If we jump back in here, I'm going to go back into the library here. Let me see if I can find a plus 5 volt power. Is there a plus 5V? Yeah. Okay. So, yeah, okay. So we've got plus 5V and then we've got plus 5V. All right. We've got a bunch of variations of that that I don't understand what those are. That's okay. just for consistency's sake, we'll use that lousy arrow that we used for the 3.3. So now one side will be one and one side will be the other. So here's what I'm going to do. Oh, I'm going to actually disconnect this wire over here by deleting it. I'm going to move this one to pin 4. So VCC will come in on pin 4. Okay. 5V will be on the input to the regulator. So now I've got something which will look like that. Okay. Now pin 2 here on this, that center pin, needs to be the power coming in here. So this one and this one should be the same. Because I'm going to use a jumper between this or this, depending on what that input is. Okay. So the way to solve that is I'm just going to wire this one directly into that. And that'll make everything really easy. Okay. Now I want to be sure, does everybody understand why I'm doing that? Okay. So this is going to be a jumper, 2 ways. I can only jump this side or this side. I can't jump both. If the center pin on that is 5 volts, I'm going to jump it to a 5 volt side. And that 5 volt will go through the regulator and regulate it to 3.3. If that's 3.3 volts, I'll jump that to the 3.3 volt side, and then I can bypass the whole regulator circuit and just drive the circuit off of the 3.3 volt inputs. So the jumper is just giving me 2 things that I can select, but the jumper can only ever be selected one way or the other. In the event that this was actually connected to 3.3, it doesn't matter if this regulator happens to be in the circuit, because it's going to bypass all of this, because the only point in which it's actually connected is out here. So it's not like it's going to cause any problems with this circuit over here. Okay? If you think about this moving left to right, the 3.3 will bypass all of that, and there shouldn't be any problems on that. So that's why I'm actually using that 3-way jumper. Now, there is a copy tool where if I click on this and then I copy my ground port, I can copy that down here. And I think, was it pin 6 that was, oh, bloody hell. I'm going to flip my component. That's all right. So I need a power port, so I'll copy that. I'll do something like this. And we'll do something like this. And I'm just using the copy tool because, in the interest of time, I don't want to have to go back to the library, figure out what's in there, figure out how to get back to those components, etc. So do this, do this. Now, this one, unfortunately, I'll break this wire here. No. And, okay. Now, you're probably going to hate me for what I just did there. But I wanted to move pin 6 to the bottom, because then I can just run this simple ground connection. So I deleted the wire between pin 4 and this for a second. I took this, rotated it 180 degrees, and then I used the mirror command to mirror it. So pin 6 is now at the bottom. So I deleted this wire, rotated this 180 degrees, used the mirror command, that'll mirror it, and now pin 6 is at the bottom, so I can draw a nice simple connection into ground. Okay? Then I can do exactly what I had before, except then I don't have to have that ground connection dragging across all of those other wires. They wouldn't be electrically connected, but I like to draw good-looking schematics. Now, I'm going to go ahead and, I'm going to have to move this up a little bit. I'm going to go ahead and draw the extra wires in here for these other pins. Now, schematic has one it's a great characteristic of schematics, but it can also be somewhat frustrating, particularly if you're sort of new to it, in that you don't actually have to explicitly draw all connection lines. The fact that this is 3v3 and it has that label on it, and that's 3v3 and it has that connected to it, those two things will actually physically be connected in PCB without me having to draw a wire between those two things. We do that just to make the schematic easier, fewer wires, less stuff to try to trace my way through it. As long as I know that this is 3v3 and that's 3v3, do I really need a wire going all the way across the page? So in this case, for those remaining 4 connections that I have in there, okay, only 2 of which I'm going to use, which are going to be my transmit and my receive, I can actually label those wires. And when I label those wires, then I'll label the same wires on the other side, and those two things will actually be explicitly connected, or implicitly connected, even though they're not explicitly connected on the schematic. Okay? So UARTs have a number of different connections on them, many of which we tend not to use anymore. Okay? So you've got DTR and ZTS. We kind of don't use those very often anymore. Okay? Typical USB to UART, the only things that we really care about are the transmit and receive, unless we're going to use things like handshaking and some of this other stuff. But we don't really have those same quality of service problems or those same sorts of concerns anymore. So what we're going to do here is instead just use receive and transmit. And so we're going to label pin 2 and pin 3. And to label it, I'm going to right-click. I'm going to choose the option here to name this wire. Okay? Well, we're going to label it, but we're going to label it after we name it. It's kind of, so the label will actually draw the physical name on it. Naming it will actually give the wire a name. That's super frustrating for me because if I label it, or sorry, if I name it but I didn't label it, I might be believing that it has some name that it doesn't really have, and if I can't see that explicitly on schematic, it drives me crazy. So, so first we're going to name it. Now, oh, I should close this because the icon is very close to what we use in Altium. So, receive from the PC side was pin 2, so we're going to call that RX_PC. We'll call this RX_PC. Now that that's named, now if I right-click on that wire and I choose label, it'll actually apply that name to it. There's a little line that it connects that says, hey, this is the wire that it's connected to. Okay? My suggestion is just keep it over the top of the wire. So we typically do it like that. Okay? Now, the other one, it's a little more complicated because, yes, technically it's the transmit line from the PC, but we're going to bring that in, and it's either going to go through the voltage regulator, or it's going to go to the other, or it's going to bypass, or sorry, not voltage regulator, voltage divider, or it's going to go directly to the pin, depending on whether or not we have a 3.3 volt input. So very similar to what we did down here below, and I'll explain this in more detail later, but what we're going to do is right-click, name, sorry, yeah, right-click, name, I'm going to call this TX-PC. Then I'm going to right-click and label. Okay? The other 2 connections I'm not actually going to do anything with. I could probably just get rid of them if I wanted. So I can right-click and delete, because we're not actually going to use them. So here's what we have now. So now we've got something which is reasonably close to what we had in the other schematic. We've got the regulator here. We've got this connector here, or the jumper here. This connector, we're going to use a right angle connector. It's going to bring our receive and our transmit in. Okay. Now this is going to have an option to go through a voltage regulator. So actually I'm going to put a voltage regulator out here with a connection in here. So I'm going to drop two resistors in here. One of them is going to be 1K, the other is going to be 1.8K. And then I'm going to draw a line which tees off of that. That'll put that through a voltage regulator in the event that I want to use, or I keep saying voltage regulator, voltage divider, in the event that I want to use the connection from the connection through the voltage divider. So, unplug my PC for a second. All right. So transmit from the PC. Oh, I was in delete mode. So I need two resistors. And there should be just some simple resistors here. And so what I'm going to do is I'll go into, those are the LT Spice ones. I don't really want to use those. Okay, so I'm going to go into R-EU, and I'll pull the resistor here, which is the 0204, which should be fine. You could use something which is slightly wider if you wanted to. Really depends on how much you want to bend the leads on them. Yeah, there's this collection, but these, yeah, there are some. I thought they were all surface mount. Yeah, there are through hole in there. Okay. So what I need here is basically two resistors, like this. Let me see. I picked R-EU 0204. And you can pick either the 5 or the 7, doesn't really matter. The 7 actually is a little bit wider apart, so you can form the leads and make them easier into the hole. But both of them should have a hole big enough to take the leads of the through-hole resistors. So it's R-EU 0207. Now I know I'm going to need a bunch of other resistors later. So I'm actually going to place a bunch of them now and just sort of shove them off to the side. So I'll end up with a bunch of resistors, but right now I'm really focused on the voltage divider here. So transmit is going to connect here. It's going to come between here and come down here to ground. I'm going to have a connection coming off of this, and that's going to be the divided down version of whatever that transmit is there. Okay? And so basically I'm going to connect those two things together like that. And now, again, I need the ground port, or the ground pin. Actually, I don't need it yet. So what we're going to do here is I need to change the values on these resistors. So again, I'm going to right-click the resistor. I'm going to smash it. Then I'm going to right-click and go into its properties, and I'm going to change the value. I'm going to call this 1K. And then just kind of move the text around. Yeah, you could just go into properties and actually do that. But the problem that what I wanted to do was actually not just display the value, but actually move the value around. So I'll go ahead in here and smash it, right-click, properties. This will be 1K8. And I'll move this. And now I'm going to place one other wire, which is coming off of here, like this. It's actually 1K8 usually. So we usually do, well, sorry, I shouldn't push that convention because different people do it different ways. I tend to use 1K8, 3V3. I don't do plus 3.3V, anything like that. And a lot of that ties into, I used to do a lot of SPICE simulation, or a lot of simulation of circuits. SPICE is a simulation engine that we can use to kind of model whether a circuit will behave one way or another. And what it does is it parses the schematic, looks for all of these names of these nets, or these physical connections between these things. If there are things like plus signs and stuff like that, they're actually problematic because they're operators. If you're feeding it into a program which does something, they're actually operators. So I tend to stay away from some of those things. It doesn't mean that, typically in that case you would do like 1.8K or something like that, but you tend to stay away from plus signs, you tend to stay away from these other sorts of things. Anyway. So I'll do something like this. And then basically I've got whatever my divided signal is going to be. So I'm going to call this TX underscore PC underscore div. So I'm going to come in here. I'll go ahead and name that, and I'll call it TX underscore PC underscore div. We'll go ahead and label it and Shazam. Now I need to put the ground symbol at the base of that. So to do that, rather than go to the library and figure out where that is, I'll just right-click on this, choose copy, drop one in here, and then draw the wire connecting those things.
You can't like hover a thing and connect it.
Sometimes. It's really finicky about some of those things. Like, I mean, in like the Altium context, if I ran a wire across these two wires over here, they would just connect. You know, if I did something like this and said, hey, I've got these things in here, would just connect some of that stuff. Here it connects it because that's actually a component pin, but normally it wouldn't do four-way connections like that. But unfortunately, Eagle sometimes flakes on that stuff, and that actually creates this sort of sense of unreliability. Like, hey, why isn't this working the way that I expected it to work? Yeah. Uh-huh.
Is it possible that you could be pasting over the same thing? Like in some type of
Uh-huh. Yeah. 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 And that happens. That happens. Some of the different CAD tools will treat that differently. Like some of them will draw a junction. If you paste two components on top of each other, it'll draw a junction where the two pins intersect. So at least you know that you have something that's lying on top of something else. Okay. So that kind of solves that problem. Now we need a two-way jumper, another two-way jumper. And basically the idea with this two-way jumper is that from this side, this connects to the PC directly, okay, if it's 3.3 volts. This side, it goes through the voltage divider. So if I jump it this way, it goes through the voltage divider first, then it connects to that pin, and this is the ESP8266. So if it's jumped this way, this connection, which goes to the voltage divider, gets jumped between here and here and runs into that pin, okay? If it's jumped this way, okay, that's a 3.3 volt situation. And in that case, then I just connect directly to that input before the voltage divider, okay? I tried to create something which creates a little bit of sophistication, so it's not just, look, let's all build another Arduino. There's nothing wrong with that, don't get me wrong. Actually, that's the basis for the workshop in San Francisco is let's build an Arduino and add BLE to it. So don't get me wrong, there's nothing wrong with that. But this kind of makes you think a little bit about the circuit. So I need one more three-way jumper, so I'm going to go ahead and just copy the existing one that I have. And I'm going to go ahead and mirror that. And now I can just do this. So one side is connected to the voltage divider. The other side is going to be connected directly to the transmit PC. There we go. And that center connection is actually going to be what connects to the receive pin on the ESP8266. Okay? So whether it's jumped this way, if it's jumped this way, it connects directly to that. If it's jumped this way, then it's going to connect only through the voltage divider, so the level will actually be divided down to 3.3 volts. The worst case is if it's jumped the wrong way, it's just going to be way too low, and you just won't get anything that's working. But at least you won't overdrive it. Okay? So, well, if you put it through the voltage divider, it won't work because it'll be below its logic 1 for the 3.3 volt rail. Because that's going to divide by, well, it's going to take it down by like a third. Yeah, so you're going to drop below whatever its logic 1 value is. So in that case, it's actually not going to cause problem necessarily because you're not overdriving it. It just won't work, which is actually okay. Like I don't mind it not working. I just don't want to break it, right? So in this case, now I'm going to put the wire in there, though I don't know really what I'm going to label that yet. And now the ESP8266 has 2 rows of pins on it, okay? 2 rows of 4 pins each, all right? So I'm going to go into the library here. And those pins are at 100 mil pin spacing. So a standard header would work, okay? So what I'm going to do is just look for header again. And collapse some of these sort of standard ones here. Now there are some female headers. The problem with the female headers is that there's not really, in the standard library, there's not really a 2x4, something like this, in the standard library. And even if there was, the way that the pin numbering is actually done on here is a little bit screwy. Because typically with headers like this, it's 1, 2, 3, 4, 5, 6, 7, 8. So odds on one side, evens on the other, right? The way that the ESP treats it, it's 1 through 4, 5, 6, 7, 8 sort of thing. So it's kind of a weird configuration. Rather than take you through the process of actually creating the component, instead we're going to use 2 single row 4-pin headers. Okay? On PCB, we'll just put them right up next to each other, so they're 100 mil spacing, not just horizontally, but then also adjacent to each other. So I'm going to go ahead and grab this part here. We'll click OK. And this is only because we don't have a huge amount of time. Otherwise, I would go in and suggest that we actually create the library component from scratch, because it would make more sense to create a library component that matched the ESP. Adafruit may have a library, but probably not for the 0.1. They have one for their version of this board now, which has the module on it, which is past FCC, et cetera, et cetera. So you've got basically, if you consider this to be row 1 and this to be row 2, let me show you a picture of what I mean here. So this is actually the pinout for the ESP8266, okay? One row, the inside row is ground, GPIO 2, GPIO 0, and receive. The other is transmit, CHPD, which is the chip enable, reset, and VCC, okay? So we're going to do these 4 on one and these 4 on another. When we put them in PCB, we're just going to put those 2 right next to each other with 100 mil spacing in between them. And then Bob's your uncle, we should be okay, and everything should be fine, okay? So again, let's go in here and so I'm going to focus first on this outer row, which is VCC, reset, CHPD, and TXTD. So actually, we tend to use J for most connectors. Yeah, I don't know if it actually came from Jumper. I don't actually know. To be honest, you could be totally right, and I wouldn't know. I don't know what it came from. So this is just going to be a lot of kind of silly naming magic, and then we're going to go ahead and add some pull-ups and some other things to these. I may actually move these back a little bit just to give myself some room for pull-ups and all of that other stuff. It's going to look hideous, but that's okay. Okay, cool. So this first one, as long as both of them start from the same side, that's okay. This first one is going to be VCC, reset, CHPD, and TXD. So it's not really going to be VCC, it's going to be 3v3. Don't worry about it. VCC is the terminology that they use. So we're going to, because it needs to be 3v3, I'm going to go ahead and copy this. And I'll just move this up here, and then I can use the move tool to actually move this back a bit, and then I'll just wire this in like this. So my first thing that I did was something like this, okay? So I copied the 3v3, and I put the 3v3 on pin 1. Pin 1 we're going to call my VCC pin. I've got pins 2, 3, and 4. And pins 2, 3, and 4 I'm going to label, and then I'll show you the schematic, and you can go ahead and duplicate what I did. So I know what I'm looking at, and transmit. Huh? Did you do it wrong? No. Sorry, I should zoom in so you know that I'm not insane, and you know why. I'm going to group some of these a little bit closer over here just for a second, just so you can see what I did. Oh. Here, move group. There we go. closer because I'd have to move into negative space. Okay, so on this one I actually named it receive PC. And I named it receive PC because I want to connect it from the transmit pin here to the receive pin, okay, on the PC. So this is actually the transmit pin from the ESP8266, but it's connected to the receive pin on the PC, okay, or on that USB to serial cable. Transmit connects to receive, receive connects to transmit, okay. So in this case, what I end up with is reset, CHPD, receive, and the this is actually connected now to receive here on this, or to this pin over here, which is receive on the PC side, even though it's transmit from the ESP8266. Now, if you want to be very explicit, you can add a piece of text if you want and just say TX from ESP8266, drop a piece of text and just kind of leave it floating somewhere out there. Now it's pretty explicit. Anybody who looks at that is going to say, oh, okay, that's a transmit from the ESP8266 connected to the receive pin over there. There's no ambiguity in that. People will look at it and understand exactly what it is that you're doing. Now, a couple of these had pull-up resistors on that. If you remember from earlier, I mentioned that the pull-up resistor is just there to put this into a known state. So if my receive pin isn't actively being pulled low, I want to know that it's actually pulled high, okay? So I placed a bunch of resistors earlier just randomly without actually wiring them in because I was placing resistors and I want to have to go back to the library. My laziness sometimes is boundless. So there are a couple of these that actually have pull-up resistors. So reset and CHPD both have 10K pull-up resistors on them, okay? So what I had done was add a couple of pull-up resistors in here, and we'll just do something like this. We'll do something like this. That makes it super easy for me to say, okay, so that's connected to that, and that's connected to that. Oh. And then if I copy this, I can drop my 3.3 volt, because I'm pulling them both up to 3.3 volts, from here to here, and from here to here. Now this is the part where I get fidgety and make sure that everything is nice and well aligned. Okay? So that actually looks like what that side is supposed to look like. Okay? Yeah, exactly. It's active low. So when you press the button and short it to ground, reset will become active.
Is there a way in Eagle to put like the bar, the bar?
Yeah, there is actually. So
I've blown things up like that.
yeah, so if I go into name, now you're challenging me with this. No, you're fine, you're fine. If you put the exclamation point in front of the word, it'll actually draw the overbar over the top of something. You just have to remember that anywhere else where that was already existing in the schematic, that you also put the overbar over it, because otherwise the two aren't connected. One is reset not active low, and the other is reset active low, right? And the exclamation point also works in Eagle if you use one as an opener and one as a closer. So sometimes you have multifunction pins on microprocessors, where one pin is this pin active low, but it's also this pin over here, and that's active high. So in those cases, when you're naming pins, it's usually when you're naming pins on new schematic symbols, that you actually use the exclamation point both before that segment and after it to just put the overbar on that section. So Cool. So I've got 4 more pins here that I've got to deal with. And those 4 pins are my receive pin, which is actually transmit. Okay. I've got GPIO 0, GPIO 2, and ground. So I'm going to give myself a little bit of room here. And the way to kind of move a group of stuff is over here in the left-hand column, you've got a command called group. And if you use a group command, you can draw a bounding box around stuff, and it'll actually group them. Now if I use the move command, and I right mouse out in free space, I can choose the command to move group, and then I can move that whole group of things together. Okay? And the group stuff is actually really, really cool for just getting a bunch of stuff together and actually making changes to it. And you can actually use them to make changes to whole groups of things as well. So if I wanted to, make a change to a collection of, I don't know, text and change all of the fonts or things like that, I can create a group. There's actually a tool in Eagle called the change tool. And if you go under change, you can change a whole variety of different things. You can also change groups of things. So you'll have options to change fonts and change sizes of things and spacing of things and yada, yada, yada. You can change groups of stuff. You can also change individual items.
Could you use that instead of a bunch of passwords, or is it just one value in the shop?
That's a good question. I'm not sure that I don't think value is in there. That's why. So you can't actually do it with value. What you can do, though, is once you're in change, the cool thing about change is that it's modal. So if I decided that I, for example, wanted to change, I don't know, font size for something, I can go into the change tool, change font, I don't know, change this to something, vector font, something like that. And when I click on these things, then I'm actually in that mode until I'm out of that mode, right? Yeah, exactly. Yeah, no, Eagle's got like 3 fonts. Comic Sans is not one of them. Wingdings. Okay, so just going back to that pinout. So ground is going to be my pin 4. Okay, so we'll start with that. We'll go back to Eagle and I'll drop that to ground. That's pretty straightforward, so I'll move this back. Again, following with my desire to build all things which look beautiful. I'll do that. I'll copy my ground from over here. Just drop it down here. And then I will draw a wire in between here and here. Okay, so that's connected now to ground. Now I've got 3 pins here, only one of which is reasonably complicated, or something that we have to think about. So I've got my receive pin. Now receive is not receive. Receive is actually the transmit from the PC side. It's the receive side over here. But we went further in complicating that because we said, hey, we want to push it through a voltage divider unless we have a 3.3 volt input. And then if that's the case, then we don't care about the voltage divider. So we actually created something which is a little more sophisticated. So what we need to do, first of all, this wire here needs to be connected to this center wire here. Okay? So we're going to go ahead and name this, and I'm just going to call this TX. I'm going to put a label on that. And I'm going to name this, I'm also going to call that TX. Those two will become connected. I'll go ahead and put a label on that. And now this wire here is now explicitly connected to that wire there. Okay, so transmit is connected to transmit. That's connected to the center pin of that jumper. And whether I jump it this way or this way, it doesn't matter. It's actually always going to be connected to that center. If there's nothing on that jumper, then nothing's going to be connected. And the worst case is I'm not actually going to be transmitting to anything from the PC side. The other worst case scenario is not that bad. My voltage level will just be too low. And so nothing will actually register, and it'll be like there's nothing on the line anyway. So you'll be sending a bunch of data, but I won't be hearing it because your voltage level is too low. So both of those situations are situations that are not catastrophic, and that's okay. I can deal with that. So go ahead and, I want to move that text a little bit. Align it with the stuff up here. You don't understand how much of this is aesthetics. Okay. So I've got transmit, which is connected to that. Cool. I'm going to do the same thing that I did earlier, and I'm going to create a label here, or a piece of text here. Oh. Oh. So that is your chip enable. Okay. So I'm going to go ahead and go into the properties of this text, and I'm going to say this is so I've got transmit from the ESP8266. I've got receive to the ESP8266. Okay? One of these is coming in, one of these is going out. Okay? I'm going to move this. I thought I moved that, but apparently not. All right. So I've still got these two wires here. Going back to the image for this, I've got GPIO 0 and GPIO 2. And if we have a look here, the way that I've got GPIO 2 is I've got the pull-up on GPIO 2. So I'm going to run one more pull-up resistor, and that's going to be on GPIO 2. And then I have GPIO 0 also connected. So we'll go here. I'll call this, let me just double check. So it's GPIO 0 and GPIO 2. All right, so one more pull-up resistor. In this case on GPIO 2, go ahead and drop a wire between these two. And then again, I'm going to go ahead and duplicate or just copy this power port here and make the connection between these things. Not bad. So far, reasonably good. Okay. So far, nothing catastrophic. Let's just put it that way. All right. Now, I had a couple of push buttons and an LED. Okay. And there was one push button, which was on GPIO 0. And there was another push button, which was on reset. So I'm going to go ahead and jump in here and I can't remember what the name of it was. Was it under switch? No, it's a bus switch, blah, 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 blah. Where is... I don't think it was switch though. I thought it was, well, that's what I did. So I did SPST, but I couldn't find it under SPST. I did reinstall my library today, so maybe I didn't install the library that had the switch in it. So I think there was an Adafruit library that had some push buttons in it, or it was the Arduino library that had push button. Actually, no, Arduino doesn't have a push button, so maybe it was the Adafruit one. Okay. Never fear, this should be easy enough. So we'll actually do this with jumpers. It's easier. Well, it's easy. So we'll do it with just 2 single headers. So I'm going to go ahead and collapse this. Yeah, apologies for that. I thought... Oh, is jumper in there? Yeah. Okay. Ah, yeah. But that's... You said the last one? Ah, that's a jumper. Really? That doesn't look like a jumper. That footprint doesn't look right. Is it just... That footprint doesn't look like a jumper. It doesn't look like it has any pins or any pads. I don't know what that's supposed to be. What's that? Yeah, so, yeah, cool. Okay. So, God, it looks hideous though. Sorry. All right, so, and go here, and I need one more, which I'm going to do here. Okay, so, just in the interest of time, sorry. So, connect this into here. Cool, all's right with the world. I'm going to connect this out here, and then I'm actually going to run that into ground. So when that's jumped, GPIO 0 will actually be at ground. Okay? Over here, likewise, when this is jumped, reset will actually go to ground. Okay? So go ahead and copy that. Here, I'll just do this. All right. That's a reasonably good looking schematic. I mean, it's, you know, it's not perfect, but it's not terrible. And we need an LED. So I just need a simple LED. So go in here, place one other component, which is going to be my LED. No. I wish I could. Yeah. Yeah, I wish I could. Unfortunately, I can't. So, through hole LED. Anybody? Anybody? Well, but that's the LT spice model, which doesn't help. All that is a voltage drop. And like, just an LED as a simulation model, right? It's just a voltage and a current sort of thing. Let's see. So that's right angle. These are all surface mount. Fortunately, the world has moved beyond our through hole. I'm sorry, I do have to apologize because I did uninstall my libraries this morning. I tried to bring Eagle back to kind of square one this morning. Cool. That's all right. I'm going to pick the dialight. I'm actually going to use this 1206. It's okay. I have surface mount LEDs, so we should be all right. Okay, so I'm going to pick the dialight. I'll do that LED 1206 green. I didn't want to have to do this to you, but we'll do it anyway. And I'm going to place one LED, which is this. And we'll go ahead and draw a wire into that, which is going to be connected to GPIO 0, and the other side, which is going to be connected to ground. And here we go. So now notice I have a bunch of stuff which exists outside of the origin. I'm actually going to group all of this, go to move, and just say move group. I'm going to smash this and get rid of that stupid piece of text which is showing there. Just hide that. And then I can get rid of these extra pull-up resistors. So that's kind of the nuts and bolts of it, right? So just to recap it while people are kind of catching up, finishing up, whatever. So this is a 6-pin connector, USB to serial. It's got a receive and a transmit on it, both of which I'm saying come from the PC, though they don't have to. They could come from Arduino. They could come from anything else. Though I will say with the ESP8266 that if it is transmitting at 400 milliamps, you're drawing more current than the 3.3 volt or the 5 volt rails will actually give you through the Arduino. Okay, so you may find that it drops out. It does weird stuff. Okay, because it can't drive it, because you don't have enough current actually going to it. So it's actually drawing more current than the Arduino is going to give it. So connecting transmit and receive is fine, but powering it from the Arduino is no bueno. So here's our regulator circuit, 5 volts in, 3.3 volts out. I've got my 6-pin connector here, and I've got my jumper here to select between whether this is a 5 volt or a 3.3 volt device. I've got the voltage divider, which connects into here. I can select between either the voltage divider side of that or this side over here. I've got the two connectors, one for each one of the rows from the ESP8266. Yeah. Yeah, sorry. So let me go ahead and, I had a bunch of resistors in here too. So you're absolutely right. So I need to put the current limiting resistor on here anyway. So I'm going to name this, and I'm just going to, let's name this LED. It doesn't really matter. This side should actually be GPIO 0.
So GPIO 0 is active high or active, it's active low?
Well, GPIO 0 is active however you want it to be active as a GPIO. Okay. But to flash with the device, you actually have to hold it low, reset the device, and then start flashing. Okay? So
this will indicate, so when that LED goes out, that means that it's ready to flash. And that LED turns off.
Right. So, well, no, because it will be stateless until you're ready to flash it, right? If you're ready to flash it, you pull it low, it's not going to turn on. It's only going to turn on if you explicitly drive it. Okay. So, okay, cool. So we've got a decent schematic. I'm going to go ahead and save that. I'm going to call this ESP8266. So that's a decent schematic for what it is that we want to build. Okay. Next step is going to be to actually generate the PCB file. So we're going to go and move from schematic to PCB just by clicking the option up here that says Generate Switch to Board. When you do that, it'll generate a PCB file. That'll be way bigger than anything you ever needed to build. And it's going to take all of these components and populate them into the PCB. It's going to say Create from Schematic. I'll click Yes. What I end up with are all of the components grouped out here. Okay. This is currently the working area of the PCB. Totally oversized for what we need. Okay. I think the original version of that board that I did is 30 by 35 millimeter. So I don't know what that is in imperial units. Something in imperial units. You guys figure it out. So we'll do it in inches. So it's 1.4 by 1.18 inches. So it's reasonably small. It's not huge. Now, let me go ahead and stretch this a bit. Now, I want to mention a couple of things about PCB that are somewhat unique to PCB than they are in schematic. Though schematic has some of these things, PCB really uses them. So PCB, remember, is a layered environment. Okay? Some of the layers are physical layers. Other layers are logical layers. Silkscreen, solder mask, top copper, bottom copper, all of those things. Those are physical layers, right? Some of the stranger translations, there is a cream layer, which apparently is supposed to mean like paste mask. That didn't translate well. There are a few of those. Stop layer in here is actually the solder mask. That didn't translate well either. So, you know, there's a whole collection of different layers in PCB. Right now, we're going to focus really on just two, which are going to be top and bottom, and then this other one here, which is the document layer. And the document layer is actually what you use to define your board outline. Okay? Right now, you have a gray line which extends the full space of like the working area of the PCB. That's actually your board outline right now, and you don't want that to be that big. Eagle makes this gargantuan thing. So what I'm going to do is go ahead and draw a bounding box around all of that, just using the group tool over here. So I'll click group, draw a bounding box around that. I'll click the trash bin to go into delete mode, then just right click out in free space and choose to delete. Now you could right click and delete and just go line, 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 line and delete all of the lines, but it's not particularly efficient. It's easier to do it with the grouping. So next thing that I need to do is just connect these things together. Now, what you see here, this collection of lines here, we refer to as the rat's nest, right? So they're just connection lines. They're guide lines, guide wires sort of thing. They're not physical connections. They're just indications of what needs to be connected. Okay? Now, I will say this. Eagle tries to group those things in the shortest path for the current placement of components. But as soon as you move components, you need it to recalculate them. And there's a tool down here called the rat's nest tool that you can hit, and it will recalculate what the shortest path is to the next thing that belongs to that net. So that sounds really confusing, more confusing than it needs to be. Let me show you an example. So if I go into move here, and I right-click and I move the group, and I kind of move this over here, I'm going to grab one of these components, move it, and let's say that I shove it over here. Okay? It's still showing this to be connected all the way over there. Maybe I'll move something like this. Maybe I'll move something like that. If I hit the rat's nest tool, it should recalculate those connection lines to be the shortest path for those connections. Okay? That doesn't mean the path that you'll typically route, but it means the shortest path. So in this case, what we're going to do is go ahead and connect some of these things together. And starting first with this connector, which is going to hang off of the far left side of the board. Okay? On the right side of the board, I'm going to have these other two connectors, which are my and we're going to have to get this just right. Now, hang on a sec. Let's figure out first which one is which. So VCC should be up. So we'll go back to schematic for a second here. So SV4 pin 1 should be VCC. That's the outermost connector. Okay? So in this case, that's correct. Pin 1, SV4, that's VCC. That's the outermost connector. Okay? If I want that thing facing this way, but I don't. I want it facing the other way. So, yeah. Oh, so from schematic, there's a little option up here. Says generate switch to board. When you click on that, that'll actually take you over to the PCB file. And it should automatically generate the PCB for you. So now that I'm over here, I actually want to switch this around because the image that I have here is with the board facing this way. But I don't want the board facing that way. I want the board facing the other direction, away from this. So we'll flip both of these around. Yeah, for sure. So in this case now I've got these two things. They're 100 mils going this way and 100 mils going this way. So my relative spacing should be just about right. Okay. Well, right now I'm just doing it based on grid. So my distance here should be, looks like it's slightly off. What's that? Right. So yeah, so if you type grid, or you click the little grid icon, doesn't really matter. You can turn the grid on. So I've got 50, 100. I picked the wrong headers. Picked the wrong headers because the holes are oblong. So technically, they would need to be like that. That's okay. I can solve that problem if I can get into the library for this. I'm actually going to modify these. So what I did is on the PCB, because these are going to overlap, I just went in, right-click, open package. When I'm in the package properties, or when I'm in the package editor, I can actually come in here and modify whatever my pads are going to be, and then reload the footprint. So I wouldn't recommend doing it, but in the interest of getting this done quickly, because I picked the wrong library, we'll go ahead and modify this. So yep. All right, I may have to change headers because I modified these. or because I picked the wrong one. So I picked the wrong set of headers. There we go. Ha 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 ha. Voila. So all I did was change them to round. So I went into change, changed my shape, went to round, bang, 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 bang. Life is good. I'll save it. Now I should be able to come in here and
So any Diff 8 package kind of fit something like that? I got 100 mils on the side.
what's that? Yeah.
They use the Stanford Diff for Diff 8 or anything?
Yeah, 100 mil spacing. So not sure if anybody saw what I did there, but basically what I did is I modified them to be round holes, and then if you come in and you do library update, it'll update those to reflect whatever the new footprint was. And I did that because the oblong pads that I chose in that library were screwy. So what I did is I went to Open Package, went to Change, changed the shape to round, click, 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 Control S to save, close it, and then Library Update. And that fixes all of that. Now I don't have those stupid oblong pads. Yeah.
I know this is a little late, but the LED through-hole ones, you can find it essentially for LED 5.9.
Oh, really? Okay. Actually, that's not too late. I would prefer to use this. Sorry? For the, do what? No. So actually what I will do though is tonight I'll actually have one milling out. We'll actually mill out a PCB. So if you're going to hang out for the party, I'll let my mill run after stuff starts and we'll actually mill out the board. It may take me a little while to get everything routed, but. So, okay, life is sweet. I've got those connectors in there. Go ahead and move these. So I'll go to move, right click. Go to move, right click, and move group. Now I kind of want to do this in a way in which they're pretty consistent with the other stuff. Now, just looking at my original board file, basically what I did was something like this. I've got the connector over here. I've got the jumper on the input, my regulator, capacitor, capacitor. I'm going to follow basically the same layout. So and the reason I'm going to do that is because the layout was then reasonably easy to do. So ignoring the big honking graphic on this thing, oh, I was going to change that regulator too, wasn't I? It starts to look pretty chaotic. Now, to actually make the connections between stuff, you're going to end up using the route tool and not the wire tool. If you use the wire tool in PCB, you're doing the wrong thing. If you use the route tool in PCB, life is good. Everything works the way it's supposed to. Okay? So basically, just looking at this board, I've got that right angle connector. I've got the header here for that two-way jumper. I've got the regulator there. And then I've got capacitor and capacitor over here. Okay? I've got the LED and a couple of resistors up here. I'm going to end up putting my jumpers on either side, my connector over here, another jumper in this. So I'm starting to create something which looks a little bit like that. And now you said it was LED 5mm? Okay. I'm going to replace the LED because I want it to be good.
So if you replace it on the schematic after you've already made that, does it automatically replace the element in the PCB board, or do you have to record that?
If I delete it from schematic, if I replace the element in schematic, it'll automatically replace what's in PCB. If I delete it from schematic, it'll delete whatever's in PCB. So the two things should stay in sync with each other. The one circumstance in which that doesn't happen is if you open up just the schematic and you modify the schematic without the board file being opened. When that happens, it turns into a complete disaster. So you don't want to do that. So LED 5mm. Ah, look at that. Sweet. Thanks, man. That makes life much easier. LED 5mm. Oh, I want to go back there. Sweet. All right. So somewhere up here will be my LED. I'm going to need some resistors over here. Figuring this out from the schematic. If I move my schematic out here, my board over here. So I've got R5, which is connected to the LED. That's up here. I've got R1 and R2, which are my voltage divider. Exists somewhere in here. Move this out of the way here a bit. Now, to route some of this stuff together, if you click the routing tool, which is over here, once you're in routing mode, you have a choice of track width via diameter, via size, that sort of thing, via geometries. So once I'm in routing mode, right now I'm on the bottom layer. There's also a top layer. When you're in routing mode, you only have the option to choose between two layers. If you're in wiring mode, and you go to the layer list, you'll get a bunch of other layers. You get a bunch of other layers because it's actually used for drawing, not for routing, okay? So wiring means drawing in one, but yeah, anyhow. So if I do something like this and just connect a bunch of stuff together. If you right mouse when you're in routing mode, it'll actually change the cornering angle and the way that corners are actually drawn. And basically, I mean, routing, unfortunately, is just one of the realities of what we have to do as engineers. Kind of sucks. I'm going to go ahead and just draw a board outline, which I think will outline the outside of all of this stuff. And then if I'm lucky, depending on the version that I have, Oh, here, yeah, if I do rip up. Oh, it doesn't allow me to auto route. Oh, I hate you, Eagle. Okay, in the interest of time, we could go through the process of actually routing this. I'll route it in a little bit. But I want to show you the process of actually generating the output file. Okay? Couple of little routing shortcuts. If as you're routing, you decide that you want to change layers, there are a couple of different ways to do it. One is to use the center mouse wheel. The other is to just hold shift and you'll drop a via. Okay? You won't change layers when that happens, but it's super convenient if you have something like a ground plane on the other side of the board, because that gives you your vertical connection through to the plane. Okay? Some of those little things are just serious performance bonuses as far as PCB is concerned. But I want to show you how to generate the output file. So if I wanted to generate output files and say drive another mill or send it to a manufacturer, that sort of thing, a couple of different manufacturers will do really low-cost boards. There's a place called Oshpark, O-S-H Park. Oshpark does boards for really, really cheap. They don't often come with solder mask on them, unfortunately. Or sorry, excuse me. They don't come pre-doped with solder on them. This is an Oshpark board. I'll share it around. Some boards come with solder already on the pads. Oshpark doesn't put that on there. The solder mask that Oshpark uses is famously purple. They're reasonably inexpensive. The cool thing about Oshpark is that they charge by area. So it's the amount of board area that you use. Their rapid turnaround is cheaper than most other places. Though I built 50 of these really small boards for about $600 on a 24-hour turn, which, oh, $600, but as compared to what? It's a 24-hour turn. There's no such thing as a 24-hour turn. It's really a 72-hour turn. You send it to them one day, they start morning of the following day, they work for 24 hours on it, and then they overnight it to you. Okay? So it's always a 72-hour turn. There's just no such thing as a 24-hour turn. I've done 4 boards easily in a day, no problem, milling them out, with plenty of time to spare. I mean, that's me designing other boards in between there and doing a bunch of other stuff on a milling machine. So that side of it is pretty cool. And later I'll actually have the milling machine running, and I'll show you how to mill.
In routing, can you route underneath the resistors?
Oh, yeah, absolutely. Absolutely. So you can route between pads, you can route underneath components, as long as you don't cross through components. And this is actually one of the big problems with Eagle. If I route a connection like this just straight across the board, I've managed to short a huge amount of stuff together, because I have now physically connected this plus all 3 component pins of the regulator, plus everything else that happened to be in the line of fire. Okay? Eagle doesn't have that normal sort of, and by normal I mean every other tool on the planet knows to stop when you get to something else. So if I go ahead and route, and I pick up from a track, this will actually prevent me from routing over the pad and actually wrap around the pad and say, no, 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 you don't want to go that way. Dude, what are you doing? You're completely insane. And I have to very explicitly tell it, no, really, I want to be insane. Otherwise, it won't let me. So typically, you want to route, obviously, around things if you can, but it's totally common to route underneath things. So I do it all the time. I mean, you'll see that with a lot of these other things where I route in between. I neck my way through pads. Here's a good example. This is a bottom layer track which necks between those pads. Now you will notice that when pads connect to these planes, they do this using thermal spokes. The reason we do that is because the pad will actually heat up when you apply soldering iron to it, or you heat it up on a reflow system or something like that. And the heat will transfer into the plane. So to prevent too much heat transfer and stop the board from delaminating, because again, you've got a heat-sensitive material which is actually responsible for bonding the layers of the board together, we actually use thermal connections, or these thin spokes, which limit the heat transfer, but still allow enough current to travel between those different things. So pads will always have these thermal connections to polygons and things like that. Sorry, I wasn't really trying to make you all nauseous with that, but You'll see these little four-way thermal connections. Eagle does exactly the same thing if you draw a polygon. If you want to generate outputs from Eagle, though, and again, I'm running short on time, so I want to be sure that we get to it. It's all done through what we call the CAM processor. And the CAM processor, basically the two fundamental outputs that you use for manufacturing are going to be Gerber and drill files for the bare board, and then pick and place files for the assembled board. Okay? So pick and place files are exactly what they sound like. They say, this is the component, this is where it goes, and this is its orientation. Okay? The Gerber files that we use are basically just a way to reduce the elements in the PCB to primitives and say, oh, this is a combination of flashes and draws that are defined by apertures that actually create the same structures in the same structures when they try to produce something with a system of photolithography. So we'll do that with, I'm going to go here and, oh, hang on, I got to save the board first. So we're going to go to File, CAM Processor. And Eagle's got some built-in CAM processors. If you just go File, Open, and you open the existing jobs, you can grab different CAM processors. They have a two-layer CAM processor. We use Gerber files. Gerber files, the current standard for Gerber files is RS-274X. The X just means that it has embedded apertures. You don't have to think much about it. Basically, if you imagine that this whole process started at one point as a process of photolithography, we have in Gerber files a series of apertures. And the apertures are related to draws or flashes. A flash of light, or you explicitly draw using a moving head something, okay? Those at one point created the film that you would use to then go ahead and mask out the areas of the board and go ahead and apply an etchant and remove the copper in the areas that weren't masked, okay? That's kind of how that process started, all right? The current convention is to use RS-274X. There is actually a new Gerber convention. There's quite a few new conventions, but there's something called ODB++ and a bunch of these other things which are much more sophisticated, have more detail. In the Eagle world, it's all Gerber 274X. So basically, you know, if I do, well, try layout to CAM, okay? When I choose this, basically what Eagle is going to do is it's going to give me, such a throwback to the 90s, it's going to give me two generated outputs here. One is component side and the other says solder side. And that's a throwback to when we only put components on one side of the board, and then we soldered them on the back side. Rip up any old CRT monitor or anything like that, and well, probably not even CRT monitors, but you know, old televisions and stuff like that, and you'll probably see that. Basically, you're going to pick whatever layers that you want output. You're going to choose the format or the device that you want to use. And the device that you typically want to use whenever you're doing anything in Eagle is Gerber RS-274X. Okay? You pick the layers that you want included in that output, and if you want to create a new output, and you do usually one output per layer of the board, so top layer, solder mask, which is top stop, bottom solder mask, bottom stop, top paste is top cream, bottom paste is bottom cream. You'll see these great things in here. I couldn't make this stuff up. So these are the layers. I know it's hard to see, but and then down here, the file, typically you use a %n in Eagle, and the %n just indicates grab the file name and append something to the end of it, okay? Now that I just clicked on a bunch of stuff that I didn't want to, let me go ahead and exit that and reload it. And we're going to open actually Gerb 274X. All right. So this is, sorry, what was it? To put, I'm sorry, what on it?
Orientation dots and those.
Oh, yeah. I mean, you could do that. Normally, you would have orientation dots, depending on what you're doing, you'd have the orientation dots in silkscreen. So, like silkscreen on the component side, I should have little dots on it. I have no idea what this monstrosity is that they actually drew this thing hanging, like, I mean, first of all, normally it would be vertical anyway. I have no idea. Anyway, it was somebody's idea of a good time. Yeah, no, and I mean, yeah, and we've done it before, but it's just not practical because it eats up too much board space. So, and it prevents you then from using heat sinks. So in this case, if you just choose process job, it'll actually generate all of the output files. And the output files, just to show you what they look like, and then I want to get, we'll take a quick 10-minute break, and then I'll get into the actual programming and stuff like that. So this is what a Gerber file actually looks like. And it's built very much on the same concept as G-code. So it's really hard to see here. Let me go ahead and put this into something where I can increase the font size. Now I'll say a couple of things about OtherMill because it's actually cool and I keep talking about it, but it's because I'm excited. I bought this new thing and I'm, I have a new toy. I don't buy a lot of new toys, so actually that's not true. I've got one of everything. Like anything gadget-wise, I've got like one of. There we go. So let's go ahead and increase the font size. So yeah, now you get a sense. I mean, it's basically G-code, right? So you've got a series of, these are your various apertures. So your various aperture sizes. Again, if you think about the old school aperture wheels, that sort of thing, we literally used those at some stage. This is the aperture code, so this would be D10. D10 happens to be this one right here, which has these dimensions. And then all of these are basically hits for D10, right? It's kind of all that it is. OtherMill will accept one of the BRD files directly from Eagle. So I can actually drop the BRD file from Eagle directly into their software and drive the mill from it. It's actually pretty convenient because it means that I don't have to do any conversion. But I will run the mill actually in a tick and show you this board actually, the board that we are building, being milled out using Gerber files actually on the OtherMill. Why don't we take a break for like 10 minutes or so, and then why don't we come back and I'll get more into kind of the ESP side of things. And tomorrow, for those people that will attend, we'll actually go through and finish up some of the layout and actually put stuff together and solder some things and all of that other stuff too. Cool? Cool. So wander around, take a break, grab something to drink. I don't know if there's anything left to eat. There should be stuff to drink behind the bar too.
So what you just did, Bob, is there a way for me to get this from the beginning?
Yeah.
Because
Hello, 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 hello. Yeah. Oh. I don't like to text. I like F2F. I know. Well, this morning you texted me. I'm like,
Your arms are live streaming right now?
yeah, well, that's all right. Did I mention I was ill? All right. Yep. Yeah, so I'll put all of that stuff up.
Yeah, because like even on mine, like my components are not connected together in Eagle, and I can't get it.
Yeah, no, and that's fine. That's fine. We'll get all of it. So by tomorrow morning, I'll put all of the files, or by tomorrow afternoon, I'll put all the files up too. Because tomorrow I'll go through and actually clean up the schematic and clean up the board and do all of that stuff. All right. If you guys want to take a seat, we'll go ahead and get started and just wrap up the last bit of this. What's that? Oh, nice. You managed to get it working?
Well, yeah, I have a voltage shifter board with like a discrete regulator so it can handle the current and everything.
Ah, okay. So all of a sudden it's like it loves itself? Sweet. Okay, why don't we go ahead and get started. I'm going to just walk you through kind of the remaining bits of this board. If you guys want to file in and have a seat. All right, so over the course of the discussion today, I talked about the ESP8266. It's a really cool device, okay? And it's made by some weird company that I don't know of. Well, I kind of know of, but it's a really cool device. It's got a lot of capability, and I want to actually take you through, before we wrap up today, I want to take you through actually flashing. I think I need more applications. I want to take you through actually flashing the device with the Node MCU firmware. And we'll actually go through this tomorrow. So for people who are going to attend tomorrow, that's great. I'll actually take you through that process. I'll try also to post some videos about flashing the firmware, though there are quite a few actually on YouTube. So basically, if you recall from the original circuit, so I've got my USB to serial, that's the FTDI chip. And the USB to serial, if I plug it into the computer, that should show up as a COM port, okay? Now, I'm going to plug it into this little board here, and I've got the jumper set on this board because the board that I was using was 5 volts. I've got the jumper set to support 5 volts. So the voltage divider now, the output of the voltage divider is actually connected now through to the receive pin on the ESP8266. And the ESP actually gets placed into the header on here, and that's basically the sum total of it. Now, what we're going to do is I'm going to go ahead and connect it. And all that stuff gets connected, life is good, everything is cool at this point. There's a GitHub repository for all of this stuff, or a number of GitHub repositories for everything ESP8266 related, okay? So I want to kind of introduce you to some of this stuff, and then tomorrow, for those people that'll be here, I'll take you through actually doing it yourself. So ESP8266.ru, this site, if I can get on internet here, yeah, we're good. This site, despite a lot of the text being in Russian, there's an equal amount of text which is in English. Whew. Save me that. And just scrolling down the list on this site, and it should auto-translate after some point. Oh, sorry, bring that over here. This is a site where we're actually going to download a piece of software. We do Explorer. We're going to download a piece of software called Explorer, ESP-Lorer. Sorry. I don't quite know how to make that sound less wonky, but the Explorer software is, as I mentioned earlier, it's designed to give you an interface to the ESP8266 through a nice little dialog that I can plug in AT commands and say, do this. Or I can plug in Node.js and say, do this. And it'll just do it. Now, it's a Java app, so it'll actually run on Mac as well as on Windows. Woohoo, because I did a bunch of stuff on Mac first when my Windows machine ran out of battery on the plane, but my Mac seems to last all day. So the actual file that I'm flashing to it basically just sets up a very little web server. And it's really hard to read the text. It's OK. You don't have to read it in detail. But basically, what it does is I give it an SSID and I give it a password. I create a string buffer and I fill the string buffer full of all of the HTML that I want to load on the page. Okay? Now, HTML loading on the page isn't like HTML loading on the page 20 years ago. So a lot of the things are actually going to be loaded into your browser rather than have to come through the ESP8266. So if I want to use something like Bootstrap, I can use Bootstrap and just include that in there, and then when the page loads, it'll actually suck in Bootstrap. But it's going to do it for the browser instance rather than having to pipe everything through the ESP8266. So I don't have to store any minified version of anything on the ESP. All I have to do is just pass it HTML, and then when the browser loads and you interact with that, it's going to download those things and actually execute it in the browser. Okay? So the other thing that you need, and that software, the Explorer software, is on the ESP8266.ru/Explorer. And somewhere in here is the download link. Here it is. Let me zoom in a little bit so it's easier to see. This is a download link hidden cleverly between two advertisements, which you just might accidentally click on and give this guy an extra 0.01 cents. But download Explorer latest. That'll actually download that software. And as I said, it's a Java app. You just download it and you just run it from the folder in which it's located. The software that we're actually going to execute, or the firmware that we're actually going to flash, is called NodeMCU. And there's a site for NodeMCU, which is just nodemcu.com. And then there's also the GitHub repository for NodeMCU as well. So the NodeMCU site has a few examples built on the page. My internet connection is a bit slow at the moment, probably just because there's a lot of people connected to Wi-Fi. That's OK. But it's got some very simple examples, toggling GPIOs, that sort of thing, setting up an HTTP client, setting up an HTTP server. There are a few other examples that I've set up. I've done a basic telnet chat client. So I could actually have chat going on between devices, that sort of thing. Really, really simple to set up. I mean, literally like 20 lines. So, I mean, like that simple. So a lot of the low-level embedded detail that you would normally be sort of inundated with, where you'd have to sit down and see and write all of these things with a lot of APIs that were provided through some SDK, you can do all of that, or you can do something much simpler, reduce it down to 8 or 10 or 12 or 15 lines or something like that, and not have to think about it. So that's actually why I really like this device, because I think it's got good support at the software level amongst people in the community that are coming at it from different directions, that are all trying to make use of this $2 chip, which totally blows me away that you can get a Wi-Fi transceiver for $2. The modules themselves are like $6, and you can buy them on Amazon, eBay, whatever. Adafruit also sells the modules, and the ones that Adafruit sells are the ones that passed FCC. And they also have some more breakout stuff on there as well. So, you know, look at the Adafruit folks. They've got some pretty cool stuff on there. Yeah, so here's an example of a telnet server. I think I had trouble with their telnet server, and I set up my own. But the NodeMCU GitHub repository has a couple of very important pieces of software that you actually need to make use of all of this. So you've got the NodeMCU firmware, okay? That's what you're actually going to flash to the device. And then you're going to run scripts on top of that. So you're going to embed Node.js inside of a Lua file, pass the Lua file, and it'll just execute that sequentially one line at a time, okay? The other thing that you need is a flasher. And the Node MCU flasher is better than most of the other flashers that are out there. A lot of the other flashers, the older flashers, didn't allow you to go past like COM port 9 or something like that, so you'd have to go in and adjust the COM port numbers and all these other things. Node MCU flasher doesn't have any of those stupid problems. So download both Node MCU flasher and the Node MCU firmware. Inside of the firmware directory are also a bunch of Lua examples, amongst other things. You can also use it with AT commands. So if you look for ESP8266 AT firmware, ElectroDragon has the latest version of some AT firmware for the 8266. Super, super cool. And that allows you to just use AT commands and talk to it over a COM port. So it's really simple, very straightforward, very easy to use. And you can push any of this stuff from, say, an Arduino forward. There's just not that much text. So even if I wanted to have a script file, it's only going to be, you know, reasonable size, right? It's a fairly limited amount of text that I'm going to pass that will do a whole bunch of stuff, and that's actually why I quite like it. So, all right, let's go ahead and actually flash the device. So I'm going to close this window here and put my money where my mouth is and try to build some hardware or build some firmware onto this device in real time. So in the meantime, let me go ahead and whoop. Okay, so here's the board, right? So that's the programmer, or the USB to serial, the programmer, it's not really a programmer, it's just level translator and some other stuff, and then the board itself. So what I'm going to do is come in here, I'm going to pick the COM port that this is actually attached to, which happens to be COM13. Under the config tab here, it'll ask me for a path to a binary file, and then I can set whatever the base address, excuse me, whatever the base address of the binary file is going to be. In this case, the latest version of the firmware that I have in that directory is here, so I'll grab that. Now, what I found is that with these ESP8266-01 modules, which are the ones that have the header pins coming off of the bottom side, that the baud rate that worked best for me, that was fast when I flashed it, was the 115-200. You could go slower, but the 115-200 was faster, was fast. So let me go ahead and put that there. Now there's a couple of things that I have to do. I've got two buttons on here, right? One button is reset, the other is GPIO 0. To flash this, GPIO 0 has to be low when the device boots up, okay? So the way that we did that with the push buttons is I can hold down reset, hold down GPIO 0, right? And then when I release reset, then I can come in here and flash it. And as soon as it starts programming, I can let go of it, okay? I'm just holding down reset long enough that when I reboot it, GPIO 0 is also held down. That'll flash it. It doesn't take too terribly long. And that'll go ahead and wander its way through. In the meantime, any questions? Sorry? Yeah, so it's all stored inside of the module itself in its own protected area. So you shouldn't really run into too many issues with like breaking the device. I made many mistakes with this device, and I seem to always be able to recover it without having to break out. My old standby is to break out a Seger and connect it into JTAG and like, you know, if all else fails, I'll just use JTAG, you know. But I haven't really had to do that. I've managed to get pretty much everything working. So this is basically the programming activity here. And over here, you'll see a little blue light flash occasionally, which is this thing sending data going the other direction. If this thing is red and solid, and you don't see any activity going the other direction, something is screwed up. So in this case, everything is cool. I got my little green check mark over here. So I'll go ahead and close that. And now I'm going to go ahead and open up, I'll actually reopen. Nothing's open here. Okay, so I'm going to go ahead and open this. As soon as I open it, what it does is, by default, it goes ahead and just tells me, hey, I actually got an answer from that. I auto-detected the firmware. Here's the actual heap size. And now if I want to run commands on this, I can go into here and under snippets, I can actually just add something, type something. So I can say, I don't know, equals node.heap. And if I just go ahead and click run, it'll actually execute on the device. Life is good. If I want to run scripts which are stored in a file, there's something called init.lua. If you save a file as init.lua, and then from Explorer you click save, it'll actually save the init.lua so that when this device reboots, it'll actually execute that file, okay? So what this is going to do is I'm going to click save on my init.lua over here. That'll write my program into there, and that should set up a very simple web interface with 2 buttons in it. It's actually using Bootstrap, so the buttons shouldn't look terrible, but they still don't look very sexy because I am not a web developer. And what they'll do is, what we'll do then is I should be able to actually interact with this device just over the network. So in this case, let me go ahead and click save. That'll save that to the device, so it's programming now. All's right with the world. Everything is actually programming. You'll get an echo of all the things that were actually programmed. Nah, it's giving me grief. Don't believe it. Says there's not enough memory. That's not true. Let me flash it again. Oh, it went a little crazy on me. That's okay. Okay, something freaked out on me. So we'll reflash it. Driving the mouse with my left hand. This feels really awkward. Okay, let me just reflash it. Something wonky went on, but it's okay. As I said, everything that I've had happen that was weird with it, I was able to recover, so.
Is that the one you passed around?
Could be. Why? What did you do to it? Yeah, well, that could be, could be the case. Could very well be the case. Though it's been surprisingly susceptible to all sorts of nonsense with it. It blew me away how durable this thing was. Yeah, why did you all have to touch it? I don't understand.
Now, how much memory does that have?
It depends on the variation of the actual device itself. So you'll have to check the data sheet to get the specs on the newest version of the device. But it's got quite a bit. It's able to, well, it's got a decent amount. It uses external flash too, so you've got plenty of extra storage for the firmware and whatnot. So.
How many connections does it support?
So, I don't remember off the top of my head. I don't remember. Was it 12? Something? I mean, it was a reasonable number. It was like, there was enough that I could do some stuff with it. I'd have to check the data sheet. The data sheet, it's interesting because the only data sheet that's available for this device says confidential across the front of it. It's like, belongs to some company. But like, they even make it available through their own company as like, yeah, this is confidential. I don't think that means what you think it means. So, okay, cool. So I've got something here. Let's go in here. Save that. we should be able to. Oh, it's giving me a bunch of grief. Yeah, you guys killed it on me now.
Maybe it should have given it a 20
Yeah, exactly.
Wait, what about your baud rate in the top?
Yeah, no, that's actually fine. So I've had nothing but success with 9600 in that environment.
It only works for me on 11.5.2.0.
Really? But now you're using a different version of it, right? So. No, but you're using a different device, right?
No, the number one.
So check it out. If I try to do, oh, now I closed it, and now it's freaking out. Let me do this because I think somebody probably killed my device.
You want mine?
Nah. Nah, I'm stubborn. You gotta. And you were able to flash it. What?
The same one you used.
Okay. Yeah, cool. So. If this fails, then yes, I'll use yours.
So an example of the observer effect since we're watching.
You know, and I can even show you the web page in which the button is actually exposed that I was turning lights on and off this morning. It's not very sexy, but it is about as far as I ever get with web pages, and then I just get frustrated. So the experience that I found, and I chatted with a good friend of mine, the experience that I found is that most people have had kind of early frustrations with trying to get these things to flash. Most of it relates to baud rate. And most of it is just that there's no, there doesn't seem to be any rhyme nor reason about which baud rates are supposed to be ideal for programming or flashing or that sort of thing. So you actually went through the process of building a level translator board for?
I just had one that
Okay. I have the level translator that I kind of always carry with me in my box here. Yeah, okay.
What you have to do is, like the cook show does, where they make a pie, they put it in the oven, and they bring out another pie.
You know what? I had that pie. And I passed it around the room. That's my problem. It came back to me and my damn pie tastes like crap. Yeah. I mean, nothing, you know, no offense to anybody. So. My pie was just fine this morning, okay? I don't know about you guys, but. So. The other problem it could be is that it was having trouble, at least earlier, trying to get on DHCP because the network is so cluttered up with stuff. So if you can all just log out of Wi-Fi for 1 minute so I can finish my demo. Yeah, I think it's just having problems getting on Wi-Fi. So, all right. Oh, try. Oh. Ah, okay. Everybody look that way.
Nobody else use that password?
Yeah, so I think the problem was is that the Wi-Fi had changed, and I was using the wrong Wi-Fi, so. So we don't have to live stream this part. I was just going to throw that out there. That's right. That's right. You know, this is karma, right? Karma's coming to get me. There I go. Had to open my big mouth about that guy with his 3-minute library load. All right, you're going to have to believe me. There we go. Ha ha. See?
Okay, I believe you.
Yeah. Oh, now he does. You know, they call that faith. They call that faith. It's just slow. I think the DHCP was just slow. So there we go. And the LED. Never mind the switching of the LEDs. That's my bad HTML. See? There you go. There you go. I would point a finger at you, but my mother says that's rude. So, okay, cool. Yeah, I think it was probably just waiting to get an IP address. It was just taking a while. But now that that's actually connected, it's got an IP address, all of that other stuff, I can safely, or reasonably safely, I should be able to just take that blue thing off, plug that into a power supply totally separately. Doesn't need the flasher, doesn't need a programmer or anything like that. And now just the little blue board is kind of everything that you need to actually provide whatever that functionality is. So now, mind you, this is pretty minimal functionality, but if you wanted to use that and plug that into anything else, you could actually use that to drive whatever you wanted. There's different versions of these too, and I'm happy to pass around some of these other ones where more I/O are actually broken out. So you could have 10 or 12 different I/O that you'd have access to, which could actually then extend some of the capabilities and allow you to do some more interesting things. There's a number of different versions of the modules. It's not really to sell you on the virtues of the ESP8266, except that it's kind of interesting. And it's really topical right now because kind of everybody who's building hardware right now, at least from the hacker sort of maker community, is riffing on this stuff, at least at some level. Hackaday did a couple of tutorials on it, or a tutorial and a couple of articles on it. There are tons of projects on Hackaday IO now that are starting to emerge with that little device. I should probably document this little board on Hackaday IO, considering that it kind of is our website, should be fairly simple and inexpensive then to add Wi-Fi to just about anything. So yeah. Anyway, for those of you that plan to attend tomorrow, I have some of those boards. We've got a bunch of other development hardware too. So if those boards are, they're kind of interesting, but I've got TI development kits, I've got Atmel development kits, I've got a whole variety of other things. If you want to come in and actually hang out with us tomorrow and kind of riff and build some stuff, you're totally welcome to do that. Yeah?
Question, how would you connect to it if you don't know its IP? Like right now it's connected to your terminal, it's telling you what IP address it has.
Right, so at some point, so you kind of have to build that into the back end of the system at some level, right? So you either have to display that at some level to the front end somewhere, or you have to be very explicit and give it an IP address, a static IP address, at least within the context of the network. That isn't going to change, well, I guess that's static, right? And then you know, from there it should be fairly easy to manage. Yeah, yeah, yeah. The other thing, like when it's an access point, it's actually kind of cool. I've got this little Wi-Fi spectrum analyzer, which gives me all of the devices that are currently on the network and like what's connected and sort of where they are in the band and all these other sorts of things. I've been using that to debug these things. And it's actually kind of cool. It's, you know, it's interesting, and they all show up as these ESP devices, sort of enumerated out on the network. But they're, you know, they're reasonably efficient for doing simple home automation type stuff, that sort of thing. It's kind of a fun device to play around with.
Do you have to program the MAC address?
You can. Okay, I think by default they have their own MAC address configuration, but you can definitely do it. The ESP or the Explorer software or Explorer or whatever it is also allows you to come in and configure all of those things over AT commands as well. So it's not purely Node MCU. So if you flash it with the AT firmware, you can come in here and say, hey, here's the MAC address, here's the SSID and the password for the access point. Go ahead and set up as an access point, and then people can connect to it, and then you can serve stuff from it. You can give it whatever station IPs and that sort of thing. All of that stuff is also accessible through the same piece of software. So it's actually fairly, like it's really well done. I was surprised, because most of this stuff, if you ever play around with any of the development tools that are out there, most of them are just, you know, there's not a really good front end, so you end up doing all of this in PuTTY, or you end up doing all of this stuff through terminal and doing it yourself. So it's like Eclipse plus terminal, and you're, you know, dumping things and pushing stuff and pulling things and blah, blah. Yeah. So this is actually, you know, it's fairly straightforward. I was surprised to see that the community rallied around this device and not something else. It's really just the cost, I think. Because it is a weird core. Yeah.
I was actually going to ask, have you done any like bare metal programming on it?
I played around with it. I mean, the SDK is actually pretty good, and that's, I think, why a lot of this other stuff has been built on top of it. It's pretty straightforward, and the entry point into it is pretty, it's high enough level that you don't have to do a lot of, if you use the SDK, you don't have to do a lot of the really nasty low-level programming. So yeah, and it's actually fairly straightforward. And I think that's actually why the community, one of the other reasons why the community kind of rallied around it, is that the SDK isn't horrible. You know, there are a lot of SDKs that are supposed to be intuitive and easy to use and aren't. And this one is maybe not totally easy to use, but it's not like so far from reality that you can't get there, right? Cool. So any other questions, anything like that? Yeah. Uh-huh. Uh-huh. Mm-hmm. So, yeah, so whenever I do that, I really don't like to split plane layers. I really don't like to split plane layers. And I don't like to split plane layers because I don't think that, you know, in the grand scheme of things, I think that's actually a bad practice because you're distributing too much, potentially distributing too much down into the plane from these different power rails and that sort of thing. So when I do the power layer is all 3v3 because most of the board is powered at 3v3. I only have a few connections, which are 1.8 or 1.2, which tend to be related to the core voltages and things like that, specific to the FPGA, but nothing else is powered off of that. So the 3v3 serves the whole board, and then the FPGA is actually powered by the 1.8 and the 1.2 rails, but its internal core voltages are derived from the 1.8 and the 1.2, and those are kept independent of that. And those tend to be really, really close to the device, and, well, as close as possible, and I don't like to put them on the splits on the plane. I would rather do big tracks and do them on the signal layer anyway. Yeah, yeah. I don't like to split planes. I think it's one of, I don't know that there's much scientific evidence to support my thinking there. But I had heard a couple of signal integrity kind of know-it-alls over the years talk about the virtues or, lack of virtues about splitting plane layers. And consensus seemed to be that splitting planes tended to create more risk that you would generate all sorts of noises and things like that. Because you've got these different planes which are now adjacent to each other where previously they weren't, you know. And they're big and very low impedance and yada, yada, yada. So yeah, I tend not to do that. And then the other challenge with any sort of split in any plane layer is that anytime that you cross a split in the plane layer, your impedance is going to change. So like, you know, one of the things that we don't do is run clock lines across splits in plane layers. And we don't do that because you don't want the impedance of the clock line to change. And that's because the impedance is calculated against, you know, the inductance and the capacitance, and the inductance and capacitance actually change when you no longer have a plane underneath it. And the split in the plane is a gap between the two plane sections where you no longer have the plane underneath it, so your reference point actually changes. And everything starts to fall apart. So all of that sort of unraveling with splits on planes, I try to avoid it as much as I can. And like I would never split analog and digital planes, anything like that, because that's just it's just a recipe for stupidity. You'll end up having all sorts of problems. Cool. So for those people that plan to attend tomorrow, as I said, there'll be a bunch of development hardware and that sort of thing. I'll try to take whoever is interested in actually, through the kind of basic process of setting up and milling a board. I'll probably actually mill a board before we leave here tonight, just because it's CNC TV. It's very, very much eye candy, and people will like it. People like to watch it. I can literally lie there. I don't know. I grew up in the generation of Saturday morning cartoons that lied, belly up or belly down on the floor watching cartoons on Saturday mornings, and only since I've owned this have I actually lied on the floor like this on Saturday morning, like, oh, look what's happening, it's amazing. So yeah, like I'm totally reliving that experience. I don't know, maybe I need to get out more, but it's certainly exciting for me. So yeah. All right, so I'll take you guys through that tomorrow. I'll show you guys how to flash some things. If people are interested, I'm happy to show you how to solder the boards together, plug some components in them, and actually build some of those little boards. If you want to plug some of the ESP modules into it, that's great. For those people that are interested, I've got a bunch of the other ESP modules. These are the 04s. They don't have the antenna built in. Part of my goal with the workshop was to actually show you, well, one of the things that I originally thought that I would do is actually take you through connecting a wire to that and then figuring out where the quarter wave was and where the half wave was and all of those other things. I think that's probably like punching a bit above our weight if you've never been exposed to that stuff. So I erred on the side of caution and didn't do that. But if anybody's interested, I've got a bunch of ESP04 modules up here, and I'm happy to give you guys one if you just want to take one as a take it and go sort of thing. It should give you something to at least play around with. Cool. That's it. So at 6 o'clock, questions, concerns, anything like that? So just protocol from what we're going to do from right now. So we're actually going to take down all the chairs, put all the tables out, change the lighting a little bit. It should be this whole total transformation. There will be a party here tonight. There will be drinks. There will be people bringing stuff. If you've built anything that's interesting, go and get it and bring it back if you don't already have it with you. There will be drinks, there will be food, there will be all sorts of stuff. I don't know if there will be me because I don't feel terribly well, but we'll see how long I last. Or there might be me, but no drinks. So, yeah, anyway. All right, listen, I'll look forward to seeing everybody either tonight or tomorrow. And thanks. 6 o'clock.
6 o'clock.
I told you.
Do that?
By skipping laying out the PCB. Yeah.
Your delivery is good, but you often, well, not, but several times, you're lowering the freight.